nothing but organizing the data in hierarchical fashion. That means non-linear. It's not in a linear, non-linear fashion. That is in a hierarchical fashion. Right. We will start with the trees. So a tree is nothing but the data which is organized in hierarchical fashion without any closed region. See, for example, let us take a simple example. So this is called a tree. This is called a tree because it is having the elements but not the closed surface. So if you have an edge between B and C, then this is having a closed surface. So this is not a tree. Right? So that's why organizing the elements without any closed region or without any closed loop, that we will call it as a tree. So here all the elements are represented as nodes. So similar to our linked list, right? So in the linked list also we are representing every element as a nodes. If you consider an array, we will call them as an elements. If you consider a linked list, we should call them as a nodes. And similarly, if you consider that as a tree, we have to represent as a nodes. So here also there are nodes. Now we will see the basic terminology of these trees. Right? The basic terminology. So if you know the basic terminology of the trees, then this concept will be very easy for you for the next sessions, right? The first one, node. So node means the element of a tree. So it is an element of a tree. It's called a node. So let us consider a tree, a simple example for a tree, so that with that example we can write everything. Right. So this is a simple tree. Okay. This is also a simple tree. Right. So a tree can have, number of elements. A tree can have a number of elements. Sorry, we should call them as a number of nodes. So every element. So here the element of a tree is called as node. So here the elements are A, B, C, D, E, F, G and H. So all these are the nodes. All these are the nodes of a tree. Root node. The starting node of a tree, we call it as a root node. Right? The starting element, the starting node of tree is called a root node, from where the branches occurs. Right? So here the starting node is A. So in the example, A is a root node. A is a root node. And one more thing we have to remember, every tree should have only one root node. So tree will have only one root node. Only one root node. Right? Next, edge. So edge means a link or a connection between one node to another node. See, here we can see different nodes, and all these nodes are connected with the means of edges. Right? So here A, B and B are connected with the help of an edge. A and C are connected with the help of an edge. B and D are connected with the help of an edge. So edge is a link or connection between two nodes. Sorry. Right? It's a link or a connection between two nodes. Now, if our tree is having n nodes, then that tree will be having n minus 1 edges. Right? If a tree is having n nodes, then it will be having n minus 1 edges. Right? See, let us consider here the example. Here the n is equal to, number of nodes is equal to 1, 2, 3, 4, 5, 6, 7 and 8. 8. So 8 nodes are there. Now count the edges. So according to our formula, so if a tree is having 8 nodes, it should have 7 edges. Let us count. So 1, 2, 3, 4, 5, 6 and 7. So 7 edges. Right? So if any tree is having with the n nodes, then number of edges for the tree will be n minus 1. Right? So this is called an edge. Then parent node. So parent node means the node which is having branches that can be that can be called as a parent. So for example, node A is having 2 branches. Okay, so A is having 2 branches, right? So B and C are the branches of A. So that's why we can call A as a parent for B and C. And C, again, B is having 3 branches, so B is a parent. Say C doesn't have any branch, so C, we should not call C as a parent. And similarly, D is not having any branches, so D is not called as a parent. F is not having any branches, so F is not a parent. So G and H are also not a parents, but E is having 2 branches, so E is called a parent. So from the top to bottom, if any node is having a branches, then that node can be considered as a parent. A node with branches. From top to bottom. Are called parents. So here we can say A, B, E are parents, are parent nodes. So we can call them as parent nodes because A is having branches, similarly B is having branches, E is also having branches, right? So here a node can have a multiple branches. That means a parent can have multiple childs. See, so these are the few terminologies: node, root node, edge, parent. Now we'll go with a few more. Child. So after the parent, we should call it as child. The next terminology is child. So child means, see, which is having branches from bottom to top. Okay, so a node with edge from bottom to top, from bottom to top, or branches of parent. We can call it as a child. Branches of node with the branches of parent, we can call it as a child. So here, see, B is having a branch from bottom to top. Okay, so this is a top to bottom. So this is a top, this is a bottom. So B is having a branch from bottom to top. So that's why we can call B as a child. C is having a branch from bottom to top. So C is called a child. D, E, F are childs. G, H are childs. So in this example, B, comma C, comma D, comma E, comma F, G and H all are childs. So a node can have a number of childs. A parent can have a number of childs. Okay. Now siblings. So a general English terminology is that siblings means the children which shares the same parent, or a children of a same parent, we call them as a siblings. So child nodes of same parent, child nodes of a same parent node, we call them as a siblings. So in this example, so B is a child of A, C is child of A. So B comma C are siblings. Similarly, D, E, F share the same parent. So D comma E comma F are siblings. Similarly, G and H share the same parent. G comma H are siblings. Okay, hope you understood this one. The children of same parent, we call them as siblings. Next, leaf node. Leaf node means the node which is not having any child is called a leaf node. A node without child. Node without child node. The node without child node is called a leaf node. So here you can observe that C is not having any childs, D is not having any childs, F is not having any childs, G and H, all these nodes are not having any kind of children, right? Similarly, coming to the B is having children, D, E, F, E is having children, G and H, A is having children, B and C, right? So the node which is without any child node, that node we call it as a leaf node. So in our example, C is a leaf node. Similarly, D is a leaf node. F is a leaf node. G and H are leaf nodes. G and H are leaf nodes. All these are the leaf nodes. Right? Then, next one. Internal nodes. So internal nodes means that all the nodes other than leaf nodes are called as internal nodes. All nodes other than leaf nodes. So that means whatever the node which is having a child, then that called as an internal node, or we can say node with child. Node with child, right? Node with child nodes are called as internal nodes. So in this example, we are having a number of nodes with the children. So A is a child node. A is having the children, so A will be the internal node. Similarly, B is having the children, B will be the internal node, and E is having the children, so E will be the internal node. So here in this example, so A, B and E are internal nodes. Okay. A, B, E are internal nodes, right? Next. Degree. So degree of a node and a degree of a tree. So maximum number of children the number of child nodes represents the degree of a node. The number of child nodes represents the degree of a node. So for example, degree of A. So node A is having 2 children. So degree of A will be 2. Similarly, degree of B. So B is having 3 children. So the degree will be 3. And similarly, the maximum degree among all nodes is a degree of a tree. The maximum degree among all nodes is a degree of a tree. So if you want to find the degree of complete tree, that implies what the maximum number of degree among all nodes. So we have to find the degree for all the nodes, and the maximum degree where we get that will be the degree of a tree. So here if you observe, so degree of B is 3, so it is a maximum. So in this example, the degree of a tree will be 3. So simply we can say the node with the maximum number of children, we can say it as a degree of a tree, right? So in the tree, whatever the node which is having the maximum number of children, that we call it as a degree of a tree, right? So if you count the number of child nodes for each node, that will be the degree of a node, right? So this is called a degree. Next, level of a tree. So each step or each hierarchical in a tree will be counted as a level. So always the level starts from 0. So every step or hierarchy in a tree is a level. So level always starts from 0. And for every step or hierarchy, level will be incremented by 1. Right? So see here, if you observe here, so this is at level 0, this is at level 1, this is at level 2, this is at level 3. Okay, from top to bottom, the level will be 0. So level starts with 0. So all the children of A will be at the same level in 1. All the children of B and C will be at the level 2. And all the children of D, E, F will be at level 3. So we call it as a step or hierarchy. So every step or every hierarchy, simply we can call it as a hierarchy, right? So every hierarchy of a tree is counted as a level. So level starts from 0. So keep on going the hierarchy, the level will be also incrementing by 1. So here in this example, the level of a tree is 3, right? Because it is having 3 hierarchies from the root node 0. So always the level of a root node is 0, right? The level of root node 0, right? So from that 0 we have to increment the levels for each and every hierarchy. So 0, 1, 2 and 3. So in this example the level of a tree is 3. Now, so one more thing is height. Height. So here the height means, so we have to find the height for a particular node. So for a particular node the height means the longest path from a leaf node to that particular node is called a height. So longest path from leaf node to that node is height. See, for example, if you want to find the height of a bee, then see, from the leaf node, the longest path from the leaf node, so leaf nodes are G and H. From the leaf node we have to find the path or the number of edges. So here there are 2 edges, G to E and E to B. G to E and E to B, 2 edges are there. From the leaf node H there are 2 edges are there. So that's why we can say the height of B is 2. And similarly, height of A, if you consider height of A, there are leaf nodes. C is having, there is a leaf node C and there is a leaf nodes G and H. From the leaf node C there is only 1 edge, and from the leaf node G there are 1, 2, 3 edges. So we have to consider the longest path. Height of A is 3. So there is a slight difference between the level and height, right? So here the height will be specified for a particular node. So that's why we have to find the longest path from a leaf node to that particular node, for which we have to find the height. So that is called a height, right? So hope you understood this one. Next, depth. So here also the same thing, but here the depth is the longest path from a root node to that node. So from top to bottom. So here the height will be calculated from bottom to that particular node, right? So here the depth means we have to consider the root node to that node, that particular node, for which we are going to find the path. So the longest path from root node to that node. So depth is also for calculating the node. So depth of E, means finding the longest path from root node to E. That means A to B, B to E. So here the depth is 2. The depth is 2. Similarly, the depth of G is root node to that node. So 1, 2, 3. So the depth of G is 3. Right? So hope you understood this one. Depth of B from root node to that node. Root node to that node. So only 1 edge. So depth of B is 1. Okay. So the depth means the longest path from a root node to that particular node. Right. Next, see, path. Path means the sequence of nodes from source to destination. Sequence of nodes from root to leaf. We can simply say from root to leaf or a source to destination. So here see, a path means, so path of A to G is, so A to B, B to E, E to G. So this is called a path. This is called path. A sequence of nodes from source to destination. This is called path. Next, subtree. The node with the children will always form a subtree, right? So node with children forms subtree, right? See here in this example we can say, I will write here. See, this is a tree and this forms another tree and this forms another tree. So this is one tree and this is another subtree and this is another subtree, right? So hope you understood this one. So every node with the child nodes form a subtree and this is also one subtree. So simply we can say this is also a subtree. Okay. So these are the basic terminologies we have to know before going to the trees concept. So these are all the basic terminologies. So I will write once all these terminologies. So hope you understood all these things. So the root node, node, edge, root node, node, edge, parent, parent node, child node, siblings, leaf node, internal nodes, degree, level, height, depth, path, subtree. So all these are the basic terminologies of a tree. See, the name itself indicates binary means binary digits. That means only two numbers, that is 0 or 1. That means two numbers. So a binary tree is defined as every node in a tree should have at most two children. At most two children. So every node in a tree should have at most two children then that tree is called as a binary tree. So see, at most 2. So at most 2 means a tree can have 0 nodes or 1 node or 2 nodes. So that means 0, 1 or 2. So if every node in a tree is having these nodes, that means either 0 or 1 or 2 nodes, that particular tree is called as a binary tree. See, if you consider an example, so we know that this is called a tree. This is called a tree. This is not a binary tree. It's a tree but not a binary tree, because here A is a root node which is having 3 children. So this is a normal tree, right? But our binary tree means every node should have at most 2 children. So see, A, B, C, this is called binary tree. Okay, this is called a binary tree. Even this is also a binary tree, because every node is having at most 2 children. So A is having 2 children, B is having 2 children, C is having 2 children, D is having 2 children, and E is a leaf node. So it can also have a 0 nodes. So E, F and G. So this is called binary tree. This is called a binary tree. So this is a difference between a tree and a binary tree, right? So there are different types of binary trees. So we'll go with that. So just remember, binary means a 2 digits. So every node can have at most 2 children. Types of binary trees. First one, full binary tree, or this can also be called as strictly binary tree. Second one, almost complete binary tree, or incomplete binary tree. Incomplete binary tree. Next, complete binary tree, or it can also be called as perfect binary tree, and left skewed binary tree, and right skewed binary tree. So these are the few types of binary trees. So different types of binary trees. So full binary tree or a strictly binary tree, and almost complete binary tree or incomplete binary tree. So complete binary tree or a perfect binary tree, left skewed binary tree, and a right skewed binary tree. Now let us see one by one with an example, so that you will be better understanding. First, full binary tree or strictly binary tree. Full binary or strictly binary. See here, every node must have two children. Every node must have two children, except the leaf nodes. Except the leaf nodes. Right? So, if every node is having two children except the leaf nodes, that is called full binary tree. So, I will show you. See, this is a binary tree but not the full binary tree, because here what's the definition? Every node must have a two children except the leaf node. So here A is having two children, B is having two children, and C is having only one children. So that's why this is called a binary tree but not the full binary tree or a strictly binary tree. So this is called a binary tree. This is a full binary tree, because here if you observe, every parent is having two children. So A is a parent, so it is having two children. B is a parent, it's having two children. D is a parent, it's having two children. Right? Here E is also a parent, it's having two children. So it satisfies the definition of full binary tree. So this is called strictly binary tree. Right? So hope you understood this one. So if every node in a tree is having two children except the leaf nodes, so here the leaf nodes are F, G, H, I and C. So except the leaf nodes, if every parent is having two children, then we can call it as a strictly binary tree. Right? Now, incomplete binary or almost complete binary. Incomplete binary or almost complete binary. So here every node must have two children every node must have two children in all the levels. So we know that levels, so hierarchy wise the levels will be incremented. So root node level is 0 and the next hierarchy will be level 1, next hierarchy will be level 2. So every node must have two children in all levels except in last level, but filled from left to right. That means first the left child should be written and then right child should be written. So in the last level, possibility in the last level, at least the left should be happened. Okay, the left should be inserted but not the right. See example. So this is a strictly binary tree. This is a strictly binary tree, but not this incomplete binary tree, because here every node must have a 2 children on all levels. So here in the 0th level, so this is the first level. So in the first level, if you observe 2 nodes are there. So for the B we are having 2 children, but here for C there is no 2 children. Okay, it's a leaf node. So it doesn't satisfy the definition of incomplete binary tree. So this is called strictly binary tree. Strictly binary tree. And so see, this is called incomplete binary tree, because in the level 0, so in the level 1 there are 2 nodes. So for the 2 nodes they are having 2 children, so B and C. So in the level 2, okay, in the level 2, I mean possibility the last level, this is the last level, because in the next level we are having only leaf nodes, right? So in the 2 there are 4 nodes, and possibly C, except in the last level filled with from left to right. So first left must be, at least the left must be satisfied. That means the elements, the nodes should be filled in the left side. So in D it is having a 2 nodes which is on the left child and the right child, and so this is called incomplete binary tree. Incomplete or almost complete. So here see, if the tree is like this, if the tree is like this, this is not incomplete, because here we are not having the left child for node E, but we are having the right child for E. So first it is filled from left to right. So first left child should be written, and then only the right child should be written. So here it doesn't satisfy the condition of almost complete tree. So this is not an incomplete binary tree if there is a node J for E node. Okay. So in the absence of this one, this is a incomplete binary tree. Okay. So hope you understood. So in all the levels, every node should have 2 children, except a possibility for last level. Okay. Now we will go with the next one, that is complete binary tree or perfect binary tree. Complete binary tree or perfect binary tree. So here every node must have 2 children in all the levels. In all the levels, or simply we can say each level there must be 2 power L nodes, where L is a level. Right. So if this satisfies, then simply we can say the tree as a complete binary tree. That means, so in each level there must be 2 power L nodes. See, so this is not a complete binary tree, because see, this is a level 0, this is level 1, this is level 2, and this is level 3. So according to the definition, for the level 0, zeroth level, there must be 2 power 0, that is equal to 1 node. Satisfies. First level, 2 power 1 nodes, that is 2 nodes must be there, right? P and C. Second level, 2 power 2, that is equal to 4 nodes, but there are only 2 nodes, so it doesn't satisfy here, right? So that's why this is not a complete binary tree. Now, so this is not a complete binary tree. This is a binary tree, but not a complete binary tree. It is a binary tree because the binary tree definition means every node must have at most 2 children. So it is having at most 2 children. So this is called a binary tree, right? So if you take an example, see, this is called a complete binary tree because, so this is at level 0, this is 1, this is 2 and this is 3. So these are the levels. So 0th level, there must be 2 power 0 nodes, that is 1 node, which is nothing but A, and first level 2 power 1 is equal to 2 nodes, that is equal to B comma C. See, if you observe 2 nodes. So at level 2, 2 power 2 is equal to 4 nodes, D, E, F, G, D, E, F, G. Level 3, 2 power 3 nodes, 8 nodes are there. Those are H, I, J, K, L, M, N and O. See, if you observe this one, so this tree satisfies the definition of the complete binary tree. So every level should have the equal number of nodes. I mean the 2 power L nodes. For every level L, there must be 2 power L nodes. So every node must have 2 children, and it completes in all the levels. So this is the definition for the complete. So if a tree is like this, this is called complete binary tree. This is called a complete binary tree, right? So hope you understood this one, complete binary tree. So this is not a complete binary tree because it doesn't satisfy this condition, 2 power L nodes in each level, right? Now we'll go with another one. Next one is left skewed binary tree. Left skewed binary tree. So left skewed binary tree means a tree should contain only the left childs. So every node should have only left childs, only the left children. So example, A, the left children is B, the left children is C, the left children is D, and the left children is E. So this is called left skewed. So this is also a binary tree because our binary tree definition is every node in a tree should have at most 2 children. At most 2 children means either it can have a 0, 1 or 2. Here every node is having only 1 children. So it satisfies the definition of a binary tree, but it is a left skewed binary tree because every node is having only the left child. Right. So this is called a left skewed binary tree. Then right skewed binary tree. Every node should have only the right children. every node should have only the right children. So the same thing, A, B, C, D, C. This is called a right skewed. It will be having only the right children. So every node will be having the right children. So this is called a left skewed. This is called the right skewed. Right? So hope you understood this one. So these are all different types of binary trees. So we have seen the definition of a binary tree, and then we have seen the types of binary trees. So in that we have seen the incomplete binary tree, strictly binary tree, complete binary tree, as well as the perfect binary tree, and left skewed and right skewed. So this is a binary tree. So this is complete binary tree. Okay, sorry. This is a strictly binary tree. So this is incomplete binary or almost complete binary. Almost complete binary. This is a complete binary, or we can say it is perfect binary. This is left skewed binary. This is right skewed binary. Right? So these are the different types of binaries. You can say this is called tree. Right? So we have seen all these things. So first, a tree. A node can consist of an n number of children. So this is a tree, and if every node is having at most 2 children, that is a binary tree. So here every node is having at most 2 children. So if every node is having 2 children except the leaf, that is called a strictly binary. Incomplete binary tree, that means every node should have the 2 children in all the levels except the last level, and that also should be filled from left to right. So this is an incomplete binary tree, and this is a complete binary tree because every level should have 2 power L nodes. That means all the levels should have, all the levels should have the corresponding nodes, and all the leaf nodes should be at the same level. This is a left skewed, so every node should have the left child only. Every node should have the right child only. That is called right skewed. Right? So hope you understood the difference between all these things. So in today's session, we'll go with the another concept that is called the tree representation. So how to represent the binary tree while implementation.
Right. So before going to the implementation part, let us recall the definition of a binary tree. So binary tree means a tree which is having every node with at most 2 children. That means every node of a tree should contain at most 2 children. That means either 0, 1 or 2. That means a maximum of 2 children. So if that constraint is satisfied, that implies that tree is a binary tree. Now we'll go with the representation part. So binary tree representation. So we can represent this tree while implementation in 2 ways. So one is using in a linear or sequential way. Second one, using list concept. Using a list concept. This is by using array concept. Right? So both are a linear or a sequential way, but first one is by using the arrays, the second one by using the list. Right? Now we'll go one by one. So first using arrays. How an tree can be represented using arrays, a single dimensional array. So we know that. So we have to follow the 3 steps while representing any tree into the array. So first one, the first step, consider the root node at index 0. Consider the root node is at index 0. That means in every one-dimensional array, the first element, that means a 0th index element, will be the root element. Next one. The left child. The left child is placed at 2i plus 1, where I is position of parent. I is the position of parent. So we know that a tree can consist of a parent, and a parent will be having children, the left child and right child. So the left child is placed at 2i plus 1, where I is the position of a parent. So if it is a root node, the root node position is 0. So the left child of the root will be 2 into 0 plus 1, that is 1. And the right child, is placed at 2i plus 2. Here also, where I is position of a parent. Right? So we need to follow these 3 rules while representing any binary tree in a single dimensional array. So the root will be considered as a 0, and then every left child will be placed at 2i plus 1, and every right child is placed at 2i plus 2, where I will be the position of a parent. So automatically the left child means this left child will be having a parent. Right child means right child is having a parent. So based upon the position of the parent, we have to calculate the position of a right child and left child. So the position of the left child will be 2i plus 1, position of the right child will be the 2i plus 2. Right? See, let us take a simple example, A, B and C. So how this can be stored in a one-dimensional array, See, let it be, these are the one-dimensional array. This is the index 0, 1, 2, 3, 4 and 5. Right? So A is a root node. Consider the first step. Consider the root node at the index 0. So simply place this at 0th index. So A is placed at 0th index. Next, coming to this B. B is not a root node. So every tree will be having only one root node, right? So the starting node will be the root node. So B is not a root node. So B is a left child of A. So A is a parent of B. So what is the position of A? 0. So position of A is 0. Now we have to find the position of B based upon the position of root or its parent. So position of B will be 2i plus 1 because it is a left child. So where here I is the position of A, so 0. So that means 1. So position of B is 1. So at the index 1 place the B. Similarly, position of C will be 2i plus 2 because it is a right child. Where I is the parent. What is the parent position of C? Parent is A. So what is the position of parent? 0. So 2i plus 2, it will be 2. So second index, the C will be placed here. So in such a way, we have to find the position of left child and right child based upon its parent position. So the first and the root node index will be starting with a 0, and from that we can calculate the positions. We can find the positions of the children, right? Let us take an example and I will give you that. We will follow the same rules. So let us take an example and we will follow the same rules. See, let us consider here A, B, C, D, E, F, G. Okay, see here A, B, C. B is having two children, D and E. D is having only one children, that is a left child. E is also having only one children, that is left child. So let us represent this one. Let us represent this one with a single dimension array. See that, write down the index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 and 17. Okay, let it be 18, right? Now see, so A is a root node, place the A at the index A. So this is the position 0. Now B is the left child of A, so it will be 2i plus 1 is equal to 1. The position of B is 1. This is a right child. 2i plus 2 is equal to 2. C. Next, D. D is a left child of B. What is the B position? 1. So here apply 2i plus 1 is equal to 2 plus 1. It's a 3. Okay. 2i plus 1. Here the position of B is 1. So 2 into 1 plus 1. So 3. So in the third position we can write it D. Here 2i plus 2. So I is a 1. Right. So here I is equal to 1. Here I is equal to 1. Here I is equal to 0. Here also I is equal to 0. So I is the position of a parent. Right. So I is equal to 1. So 4. At the 4 we can write E. Here again, so I is equal to parent of F, D, so I is equal to 3, right? I is equal to 3, so 2i plus 1 is equal to 2 3s are 6 and 7. So position of F is 7, so here it will be placed. And G, I is equal to 4 here, so 2i plus 1 is equal to, because it is also a left child, so 2 4s are 8, 9, so 9th position. So G. Okay, So this is the array representation of the given tree. So hope you understood this one. So these will be in empty. These are all will be the empty, right? So both are having only the left childs. So we have to apply the formula 2i plus 1. If it is having the right child, we have to apply the formula 2i plus 2, where I will be the position of parent of f, that is d. D position is 3, right? So from the root node, we have to calculate this and we have to fill the array. So this is how we can represent an binary tree into this array representation. So hope you understood this concept, right? So we have to follow the 3 rules. Root will be 0, root will be at the index 0, and the left child will be at 2i plus 1, right child will be at 2i plus 2. So simply following those formula, we have to represent the tree in array format. Now we'll go with the second representation, second type of representation. So that is list representation. List. So here we will use a double linked list. A double linked list, right? For representing each node. For representing each node, right? So double linked list means we know that it is having 3 fields, right? 3 fields. This is a node, or this is we can say this as a data or information. This is the address of previous, here the address of next, right? So this is how we can represent a node using the double linked list. So here we need to represent the binary tree. If you want to represent this binary tree, see, we can consider a node with the 3 fields. See, with the 3 fields. So this is a data, and this holds the address of left child, and this holds the address of right child, right? So every node of a tree can be represented by using this one. So a data, it is a address of left child, address of a right child. So this is how we can represent a tree, right? So let us take an example. Hope you understood this one. So let us take an example. So consider an example, this one, A, C, F, G. Okay, so this is a binary tree because every node is having at most 2 children. Now representing using list. So consider the root A, right? So this holds the address of another child. Okay, so that is B, and this holds the address of another child, that is C, and this holds the address of another child, D. This holds the address of another child, E, and this holds the address of another child, F, and this holds the address of another child, G, right? So this is how we can represent the tree. So this is the address of B, here address of C, here address of D, here address of E. Here address of F, here the address of G. So A of B means address of node B. Okay, right? Address of node B is represented as A of B. Similarly, A of C, A of D, A of E, A of F, A of G. Whereas these are the leaf nodes. Observe. So D is a leaf node, E is a leaf node, F and G are leaf nodes. So this will be placed with null. So there will be no address, further address, right? So all these are the null. So this represents a null. Okay, so hope you understood. So this is another way of representing a binary tree using list. So one is using arrays, another one is using list. In the arrays we have to use the formula 2i plus 1 and 2i plus 2. So here we can use a double linked list for representing each node of a tree, of a binary tree, right? Binary tree, because binary tree means every node will be having at most 2 children. So one is the left child, another one is the right child. Tree traversals. So we know that our tree will be having a different nodes and how to traverse each node of a tree. So this traversals is of 3 types. So in 3 different ways we can traverse the nodes of a tree. So first one is an in-order traversal. Second one, pre-order traversal. The third one, post-order traversal. Right. So these categories are differentiated with the help of a root node. So based upon the root node, we can know whether it is an in-order traversal, pre-order traversal, or the post-order traversal. So coming to this in-order traversal, so first there will be a left child, and then the root node, and then the right child. Left child, then root node, then a right child. So same will be appeared for the subtrees also, right? So we will go with an example later. So first we have to traverse all the left childs, and then the root node, and then the right child. Coming to this pre-order, the name itself indicates pre-order. That means first root node which will be traversed. After that the left child will be traversed. After that the right child will be traversed. Coming to the post order. Post order means the root node will be at the last. So first left child, right child, and later the root node. Right? So this is how we can apply this traversals. So that means traversing the nodes of a tree. Now let us take an example of 3 nodes A, B and a C. Let us take an example. This is a binary tree, right? Because so all the nodes are having at most 2 children. So not more than 2 children, right? So coming to this in-order traversal of this tree, first left child. What is the left child? B here. So B, then root node A, and the right node C. So this is the in-order traversal of given binary tree. Coming to this one, pre-order, with the same example. Pre-order, root node A, left node B, right child C. So this is the pre-order traversal for this given root node. So we have to visit all the nodes. We have to visit all the nodes. Coming to this post order, first left child B, right child C, root node A. So this is the post order traversal for the given binary tree. So this is how we have to visit the nodes. So the order to visit all the nodes. So first in order, first we have to visit all the left childs, then the root node, then the right child. In the pre-order, first we have to visit the root node, then left child, and then right child. And in the post-order, first left child, right child, and the root node. Now we will take one example and we can solve, right? So what is a pre-order traversal, what is a post-order traversal, and what is the in-order traversal, right? So we will go with an example. I will give you the example. A, B, C. Okay. So this is a simple binary tree. Now we'll go with another one. Right. So it is having only one left child, and it is having two children, E, F. Okay. Here for P it is having only one children. Okay. Then E is having only one children, that is also right child. Next. Right. So this is a binary tree because here also every node is having not more than two children. Okay. So at most two children. So here the node, every node of a tree is having at most two children. Now coming to this in order. In order means left, root, right. Right. So coming to the left. So here A is a root node. This one is a left subtree, and this one is the right subtree. Okay, coming to the left subtree, first we have to work with the left subtree. So again B is a parent or a root for this subtree, so it is having the left D. So first we have to write the left, so D, and then root for D. What is the root? B. What is the right child? There is no right child, so this subtree has been traversed. Okay, then the leftmost of A is completed. Now root. What is the root? A. Now right. So again right is having the subtree. Right. So C is root node for this subtree. C is a root node for this subtree. So here also we have to apply the left root right. So root. This is the right subtree. Again this is having the right subtree. Okay, so this is having the left subtree, and this is the right subtree. Again it is having E is having a root because E is a parent. It is having again subtree. So first we have to write the left of that E, which is not there. So root, that means E, right, G. So this completed. Okay, this is all the left child of C. So this is completed. Next root means C. Okay, C. Now coming to the right. Right is having again subtree F, H, I. F is a parent. That means it is a root. Right? This subtree, for this subtree F is a root. Okay. So we have to apply the same thing. Left, root, right. So H, F and I. Right? So A, B, C, D, E, F, G, H and I. Okay, so this is how we have to traverse all the nodes of a tree in order traversal. pre-order traversal. Okay. Pre-order traversal. Pre-order traversal means, so pre-order. Pre-order means first we have to write the root, left, and then right. See, if you observe here, the root is A. So first we have to write the A, and A is having this again a left subtree. So in that left subtree, B, D. B is a parent, so B, D is also again one more left subtree. So I will write this here itself. Okay. So this is one more subtree. So in that, first we have to traverse the root. What is the root for this subtree? B. So B is a root. Then left. What's the left? D. Then right. There is no right child for root B. So leave it. So move on to the right. Okay. First root, left. We have completed the left traversal. Now move on to the right traversal. So right is having again subtree, where C is a root node for this subtree. Again, C is having two children, E and F, which are having again the children. So this is one subtree. So this is again one subtree, and this is again another subtree. Okay. So for first we have to apply the root. So we just write the C because it is a root for this subtree. Go with the E. E is again having children. So first we have to write the root. So E will be written, and then left. E is not having any left child. So leave it. Then right children. So G. So all the left subtree of C has been traversed. Now go to the right subtree. So right is having again a subtree with F, G, F and H, I. So F is a root of H and I. So first we have to go with the root. So that's why F, then left child H, and the right child I. Right? So A, B, C, D, E, F, G, H, I. So we have traversed all the nodes of a tree. So this is how we have to calculate this. We have to find the pre-order traversal. Coming to the post-order traversal. Post-order traversal means the root will be visited last. So first left should be traversed, then right should be traversed, then root should be traversed. So we have to apply the same thing for the subtrees also, right? So coming to this complete tree, A is the root. Okay, what is the left child? So this is the left subtree. Left subtree. So first we have to traverse the left. So we have to consider this left subtree. So in this left subtree, again there is another subtree with B and D. B is a root now. In this subtree, B will be the root. So first left child should be traversed. So left child is D. Then right child should be traversed. What is the right child? So right child is, there is no right child for node B. So leave it. Then root. What is the root? B. Okay. This is the left subtree of A. Now we have to go with the right subtree of A because A is a root which should be traversed last. So we have to go with the rightmost subtree. Here we are having the subtree with the root C, and again we are having two subtrees with the root E and root F. So coming to the left. So left subtree of C, that means this one. So here again E is a root for this subtree. First left, there is no left child, so leave it. Then right child G. Okay, then root E. This one completed. Now move with the right subtree of C. For the right subtree of C, there is another subtree with the root F. F, H, I. First left, that means H. Right, that means I. Root, that means F. And finally, this left subtree has been traversed, so root must be written. So root is C. C, and with the C, the complete subtree of A has been completed. So finally, the root should be visited. So A. See, A, B, C, D, E, F, G, H, and I. So here also we have traversed all the nodes. So this is how we have to calculate the INORDER, PREORDER and a POSTORDER. Based upon the root, we have to divide the subtrees, and for each subtree we have to apply the same formula. So that means if it is an INORDER, left, root, right. If it is a PREORDER, root, left, right. If it is a POSTORDER, right, left, right and root. Right? So hope you understood this one. So let us take one more example, so that if you are having any doubts, so everything will be confirmed. Right. So let us take an example. A So let us take this subtree, this binary tree. So this, if you observe, this is a complete binary tree because all the levels are having, every node is having 2 power L nodes. Okay, every level is having 2 power L nodes. Right. So now we have to apply the pre-order, in-order and post-order for this subtree. So let us take in-order. So in-order means left, root, right. So let us take this one, left, root, right. First, A is the root node. So all these are the left subtree and all these are the right subtree. So coming to the left subtree, again this is also a tree. Okay, so B is root node here. So first we have to traverse this left subtree, then we have to go with the right subtree. So in the left subtree, again B is a root. This is the left subtree. This is the right subtree. Okay. So coming to this left subtree, again we have to apply the same thing for subtree. Okay. So we have to apply the left, root, right for the left child of the subtree B. So left, that means this one. So again this is having a subtree with root D. So left, root, right. So H, D, I. So we have completed the subtree, left subtree of B. Now root, root means B. Now right subtree, right subtree also we have to write left, root, right. So J, E and K. So all the left subtree has been traversed. Now root A. Now coming to this right subtree, again we are having 2 subtrees. Right? So for C, so one is F, another one is G. Coming to the same, apply the same for C subtree. So again left for C means this one. So F is a root node again because this is a subtree. So again left, root, right for this one. So left L, root F, right M. Again root for this subtree is C. So C. Again coming to the right. So right subtree again follow the same thing, left, root, right. So N, G, O. So this is the in-order traversal of the given subtree, given tree. So we'll go with the pre-order. Pre-order means first we have to traverse the root, then the left, then the right. So we have to apply the same thing for all the subtrees. So first let us take the A. A is a root. So first A will be traversed. Now left means this one. Again in the left there are one subtree with a root node B. So write down the B here. Again for B there are 2 childs, 2 subtrees, left subtree, right subtree. Left subtree the root is D. Again write the D. So again it is having a child, left child H, right child I. This completed. Now coming to this one. Here also root left, right. So E, J, K. Complete left subtree of A has been traversed. Now coming to the right subtree of A. Right subtree of A, see, again C is the root node. So we have to traverse C because it's a preorder, C. Coming to the left child, again subtree. For subtree, F is root. So F, L, M. Coming to the right subtree, G, N, O. Right? So this is the order for the preorder traversal. Okay. Coming to the post order. So just we have to remember one thing, that is we have to apply the same rule for all subtrees. Right. So left, right and root. For the pre or post order, left, right and root. So coming to the left subtree, so B is having another subtree. B is having two subtrees. One is a left subtree, right subtree. Left subtree is D, H and I. In this D, H, I, what is the left child? H. Right child? I. Root D. So left subtree completed. Now right. So right subtree. In the right subtree again we are having subtree with E, J and K. Here we have to see the left right root. So J is a left node, right node K, root node E. So we have completed left tree, right tree. Now root. That means B. So we have completed the left tree of A. Now go with the right tree of A. In the right tree of A, we are having another subtree with two childs. So left subtree and right subtree. Coming to the left, F is a root. So L is the leftmost one. F is the root. So L, M, F. So we have completed the left subtree. Go to the right subtree. In the right subtree also we have to apply the same thing, left right root. So right subtree, N, which is a left subnode, left node, right node, root. So we have completed this one. So what is the root for all these two subtrees? C. So next C. So here we have completed the right subtree of A. So A is a root. Now finally A, we can write A here. So this is the post order traversal. So for simple example, for this, right. So for this tree, these are the INORDER traversal, pre-order traversal and post-order traversal. Just we have to follow the rule left root right, root left right root. So all these should be followed for all the subtrees. Right? So this is a very simple concept of a tree and also very important concept of a tree. Traversal. And today's session we'll go with the one more concept, that is construction of an expression tree. So if you have an expression, how to construct a binary tree, right? See. So here, before constructing an expression tree, first thing we have to remember, so every operator must be an internal node, right? So that should be represented as an internal node, not a leaf node. So other than the leaf nodes, everything will be considered as an internal node. That means any node which is having children, that node can be called as an internal node. So this we have seen in the terminology, tree terminology, right? Then operands. All the operands must be leaf nodes. So in an expression tree, all the operators should be represented as a internal nodes and all the operands should be represented in a leaf node, right? So this we have to remember first. Now we know that any expression can contain only these two, operators and operands. And also we have seen the postfix evaluation in the previous sessions, right? So before construction of an expression tree, first we have to convert the infix expression to postfix expression, and that will be very easy to convert the expression tree for a postfix expression. So first we have to convert the infix expression to postfix, and then for the postfix expression we have to construct the expression tree. So hope you understood, right? So we can directly construct an expression tree from the infix expression, but so it would be very easy for constructing the expression tree from the postfix expression, right? Now, so I will give you the link of postfix infix to postfix conversion, so that once you go through that, so before watching this video. So first step, the convert infix expression to postfix expression. The first step must be the conversion of infix to postfix. Second, now we are having the postfix expression. Read all the characters. From postfix expression. Right? So reading all character means, so we'll get both the operands and operators. Everything will be treated as a character. So we have to read all the characters from the postfix expression. Next, if the character is operand, that means other than operator, right? Then push it into stack. So push that operand into stack. So all the operands should be pushed into the stack. So this is a operand stack. If the character is operator, then the first step, step 1, what we have to do? Pop the topmost two elements from stack Step 2, consider operator as a root node and construct tree with elements as right child and left child. So whatever the elements we are taking from the stack, those elements, consider one as a right child and another as a left child. Consider the operator as a root node. Step 3. After constructing a tree, push the tree as an element into the stack. So after constructing a tree from the step 2, then push the tree as an element into the stack, right? So repeat the process until reading all characters. From postfix expression, right? So these are the steps we are supposed to follow while constructing the expression tree. So first we have to convert the infix expression to postfix, then read all the characters from the postfix expression, and there is only two possibilities. One will be the operand, another one will be the operator. If it is an operand, then push it into the stack. Otherwise, definitely it will be the operator. So if it is an operator, you have to follow the three steps. So first step, pop the topmost two elements from the stack. And step 2, consider the operator as a root node, and whatever the elements we are popping up from the stack, treat them as a right child and the left child. Right? See, consider the operator and construct a tree. So we have to construct a tree in the second step. In the third step, whatever the tree we are constructing, push the tree as an element into the stack. Next, repeat the process until reading all the characters from the postfix expression. So this is the steps we are supposed to follow while constructing the expression tree. Now we'll go with the example so that your doubts will be clarified. So very simple. Example. So let us take a simple example. So if the expression is A plus B, if the expression is A plus B, first convert into postfix. Postfix expression A, B plus, AB plus. So three characters are there. Now repeat the process first. First consider the A. So take the stack. A is an operand, right? A is an operand. So push into the stack. So this is the stack. This is the character, right? Now B. Again push it into the stack. So A and B, right? Next plus. So pop two elements from the stack. So A, B, right? A and B. So consider plus as a root node. Consider plus as a root node. So consider the two elements as left child and right child. So this one. Consider the two elements as a left child and right child. So A and B. So this is the, and push back into the stack. Push back into the stack, right? So A, B. Next. So we have completed the reading all the characters from the postfix expression. So the equivalent expression tree for this expression is plus A and B. Right? So simple thing. We have followed the same rule. So first we have reading the character. It is an operand. So push it to the stack. Next read the second character. It is also an operand. Push it to the stack. And the third, it is an operator. So pop two elements from the stack and construct a tree with a plus as a root node. I mean the operator as a root node and the popped elements as a left child and right child. And push back into the stack. And if we complete all the elements of all the characters of a postfix expression, then whatever the element which is available in stack, that is a tree, expression tree. Right? So simple process. So hope you will go with the one more example. let us take an expression as a plus b star c minus d. Okay, a plus b star c minus d. Then the equivalent postfix expression. So I will just give the link in the description. So go through that link. So I am directly writing the expression, right? So CD minus and star. So this is the equivalent postfix expression for the given infix expression. Now let us take the here. So it is a character. Next, stack, right? So first read the character A. So A is an operand, push into the stack. Next, operator B. A and B, right? Next, the operator is plus. Operator is plus. So operator is plus means, see, we have to pop the elements. Yes, I have popped the two elements. So one is the left child, another one is the right child. Then consider the operator as a root node, construct the tree and push back into the stack. So I am pushing it into the stack. Right? Next, C. Push into the stack. So keep the expression as it is, right? A, B, C. Right? Right. So next D. D is a character. Again, push it into the stack. So plus A, B, C, D. Right? Now the stack is having three elements. Next, minus. Minus. So minus means we have to pop two elements, two topmost elements. So C and D. So construct a tree. Right? So C, D with the operator as a root node. I have constructed a tree and push it into the stack. So I am pushing it into the stack. See, now the stack is containing two elements. Okay, hope you understood this one. We are taking two topmost elements C and D and constructing the tree with the help of, by taking minus the operator as a root node. So again we are pushing it into the stack. Now stack is having two elements. Again now star. Star. It is an operator. So we have to pop the elements from the stack and consider this as a root node and consider this as a left and right chains. So see, star plus minus A, B, C, D. Right? So this one is a expression tree for the given expression. Right? So hope you understood this one. Simple thing. So if it is an operand, push into the stack. If it is an operator, construct a tree, pop the two elements and construct a tree and push back into the stack. That's a very important thing. Right? Now we'll go with another example and then we will wind up. Okay. Yeah. Yes, we'll go with one more example. A plus B star C divided by D. Okay, A plus B star C divided by D. So there are four operators. Yes, oh no, sorry, four operands and three operators. This is the equivalent. This is the equivalent postfix expression. Right? Now let us consider the character and the stack. Right? First A. So consider a stack with only one element A. Next character B. So push it into the existing stack. Next character C, push it into the existing stack. So now a stack is having 3 elements. Now stack is having 3 elements. Now star. So it is an operator. So we have to pop 2 elements. So C right. So C, B and C. Make this as a root node. Construct the tree. Push into the stack. See, this is a stack. Stack is having 2 elements. One is A, another one is a tree. Now D. Next D. So we have to push the D here. Right? Now our stack is having 3 elements. Now divided by. Divided by is it's an operator. So we have to pop 2 elements. That means one is a D, another one is a subtree. And make this as a root node. So make this as a root node. Right. See, I have taken this division as a root node, and this is a left child, this is the right child. Okay, this is a left child. So this element is a left child. This element will be the right child. Now, what is that? Plus. So what we have to do? Make this plus as a root node, right? So this is a right child. Okay, so this is a right child. Right. So this will be the left child and right child. Right? Correct. Yes. Right? So this will be the left child, this will be the right child. Okay? This will be the left child, this will be the right child. So here also, first one is the right child, second one is the left child. So the same thing. So this is the equivalent expression tree for the given expression. So here you can observe, in our examples we can see that operators are the internal nodes and operands are the leaf nodes. See, operators are the internal nodes. So internal node means they will have children. So plus operator, so there are children. Divided by, there is a children. Star, there is a children. And operands, that should be a leaf nodes. So that means no children. So A is a leaf node because there is no children. D is a leaf node, no children. B and C, leaf. So there are no children. Right? So hope you understood this construction of an expression tree. So it's a very simple if you follow the steps. And once again, I am repeating that it would be very easy for constructing an expression tree for the postfix expression. So first step, let us convert the infix expression to postfix expression. So that conversion link I will post in the description section. So just go through the video and then this video will be, this session, this concept will be easily understandable. So in today's session we'll go with the construction of a tree with the help of the pre-order traversal and in-order traversal.
elements. So here we will be having the INORDER and the PREORDER. So with the help of this INORDER and the PREORDER, we are supposed to find the tree. So let us take an example here. The pre-order traversal of the tree is A, B, C. In-order traversal of a tree is B, A, and C. Right. So let us assume these are the inputs we are having, and based upon these inputs we have to construct a tree. So we know that pre-order means, the pre-order traversal means first we have to visit the root, then left, then right. This is the pre-order traversal. So how these nodes will be visited? Next, coming to this in-order traversal, first we are supposed to visit the left node, and then followed by root node, and followed by right node. Right? So this is very important. And from these inputs, we know that if you observe the pre-order, where will be the root element? The first element will be the root element. So here, what is the root element? Obviously, A will be the root node. So let us construct it. A will be the root node, right? And followed by left and right. So B is the left child, C is the right child. B is a left child, C is a right child. So with the help of in-order, we are supposed to find which is the left child and which is the right child. Here there is only two nodes, one is the left and another one is the right. So if our in-order traversal or a pre-order traversal is having a more number of elements, then with the help of in-order, we are supposed to find the next root. Okay, so let us take one more example with the more than 3 elements, and so that you will understand clearly, right? Right. So let us take this example. So in this example, we can find a more number of nodes. So with the help of a pre-order and in-order, we are supposed to find the tree. Now, so let us follow the same steps. So from the pre-order, we will get the root node. From the in-order, we will get the right child and left child. So the same thing we are supposed to find. Now coming to the first one. So let us find the pre-order. So with the help of the pre-order, the first we will find the root. So in the pre-order, the first element is the root. So here A will be the root. A will be the root. Now we have to find the right children and left children. So coming to the right children and left children, that can be known with the help of in-order. So coming to the in-order, A is here. So whatever the elements left to that root are a left subtree and right to the root are right subtree. So here these are the elements H, D, I, B, E. Here are the elements F, C, J, G. And there are 5 elements to the right and left, and 4 elements to the right chain. So in that 5 elements, first again we have to find the root. So to finding the root, we have to take the help of pre-order traversal. So in the pre-order traversal, we can find these are the left child and these are the right child. So the root of a left child is B and the root of right child is C. Hope you understood this one. Okay, because here in the pre-order, the first root node is visited. So the first node will be the root node. B is a root node, C is a root node. Again, see, after B, there are again 4 elements. So H, D, I, E. And here also F, J, G. So we are supposed to find the left and right childs.
So here we know that B is a root node. So B is a root node. So whatever the elements left to the B are left child. So HDI. Okay. So HDI are the left child. Next E is a right child. Okay. E is a right child. Right. Next, similarly, coming to this one, C is a root node. So whatever the elements left to the C are left child. So F is a left child, and followed by J and G. Both are the right childs. Right. In the HDI, again we are supposed to find the root of this subtree. So in the HDI, preorder, HDI, right? D is a root node. D is a root node, and from the INORDER traversal D, the left one is H, right one is I. Hope you understood. And here also J and G. So from the preorder J and G, see two elements G, J. So first one will be the root in the preorder. So G will be the root in the preorder. Next J, left. Sorry, G, preorder G is a root, and coming to the INORDER, see G is a root, J is on the left side. So yes, so just this is a tree for the given INORDER and the preorder traversal. Just to follow the two steps in order to find the root. Just observe the preorder traversal, and in order to find the right subtree or a left subtree or a right child or a left child, go with the INORDER traversal. Right. So in the previous session we have seen these INORDER and preorder traversals, how to find these INORDER and preorder traversals. Right. So I will just post the link in the description section. Just go through the link, and then this process is easily understand. The preorder traversal. So in this session we will go with another concept, that is how to construct a tree with the help of INORDER traversal and the postorder traversal. Right. So we know that INORDER means, I will write here, INORDER means the first left child will be visited, and then the root child will be visited, and then the right child will be visited. And coming to the postorder, first the left child will be visited, then right child will be visited, and at last the root child will be visited. The last one will be the root. So here in the postorder, from the postorder we will find the root node, and from the INORDER we will find the right and left. Right child and left child. The same thing we will follow. So in the previous session we have seen, if it is a preorder, from the preorder we will get the root node, and from the INORDER we will get the right child and left child. Here also the same, but from the postorder we will find the root node. So we know that in the postorder the last element will be the root node. So if you know the root node, then from the INORDER we can know what is a left child and what is a right child. Let us take an example. So INORDER,
post order. Right. So this is an INORDER and a post order. Now we have to find the tree. We have to construct the tree. So from the INORDER, from the post order, we have to find the root. So here from the post order, see, post order is left, right, and root. So last element is the root. Sorry, the last element will be the root. So here the last element is A. So A will be the root here. Right. So after knowing the root, we have to find the right and left childs. So for that we will go with the INORDER. So here A is a INORDER. So A is a root because in INORDER the left, root and right. So all the left childs will be visited, then root node, then right child. So with the help of root node we know that what is the left child and what is the right child. So here you can observe A, this is a root node. All the elements which are on the left are left subtree. All the elements which are on the right are right subtree. Here only two elements, one element in each side. Right. So B is a left child, C is a right child. Right. So hope you understood this one. So this is a very simple. So with the help of a INORDER and a post order we can construct a tree. So with the help of a post order we will find the root, and with the help of INORDER we will find the left subtree and right subtree, and we will repeat the same process. Right. So we will go with another example. Right. So let us take this example. So INORDER and the post order. So here for root node, first we have to go with the post order. See, in the post order, left, right, root. So last element will be the root. So 1 is a root here. And now we are supposed to find the left childs and right childs of this root. So that can be done with the help of INORDER. See, here 1 is here. So whatever the elements on the left hand side are, those are the left childs. Right hand side are right childs. 6, 3, 7. So among these 4 to 5, again we have to find the root node. That can be done with the post order. So 4 to 5. See. So 4 to 5. So in that it's a post order. Post order means left, right, and root. So what is the last element? 2. So here the 2 is the right element. I mean root element. Right. So coming to the 6, 3, 7. In the 6, 3, 7, what is the last element? 3. Because the last element will be the root. 3. So 3 is a root on the right subtree. Now again there are two elements 4 and 5. Here 6 and 7. And we are supposed to find the root and then left and right childs. So here we have find that 2 as a root. Now we have to find whether 4 or 5 as a left childs or right childs. So for that we have to take with the help of INORDER. So go with the INORDER. 2 is a root node. So 4 is on the left side, 5 is on the right side. So 4 will be the left child, 5 will be the right child. Coming to the 6, 3, 7. So 3 is a root here. So 6 is on the left side and 7 is on the right side. Right. So hope you understood this one. So with the help of the post order we will get the root, because root is the last element. So here in the post order the last element is 1, so 1 will be the root element. So in the INORDER, left, root, right. So coming to with the help of a root node, all the elements towards left side to the root are the left subtree, right side to the root are the right subtree. So 4, 2, 5 and 6, 3, 7. Again in the 4, 2, 5, again we have to find the root. So with the help of a post order, 5, 4, 2. So last element will be the root. So 2 is a root node. Similarly 3 is a root node. So coming to the INORDER, 2 is a root node. So 4 is the left to the 2 and 5 is the right to the 2. So left child is 4, right child is 5. Here 3 is a root node, 6 is the left to the 3 and 7 is the right to the 3. So 6 is the left child and 7 is the right child. So hope you understood. This is a simple tree construction with the help of INORDER and a post order traversals. Right. So let us take one more example and just wind up. See, let us take this example. So there are more number of nodes, and now we have to find the
binary tree, construct the binary tree. So with the help of post order, we have to find the root. In the post order, what is the last element? A. So A is a root node. Now coming to the right and left childs, go with the in order. So A here. So there are more number of elements or towards the left and towards the right. So just divide it. So what are the elements here? H, D, I, B, E. 5 elements. Here F, C, J and G. 4 elements. So among these 5 elements, again we have to find the root with the help of post order. So in the post order, see H, D, I, E, B. So here post order, the last element will be the root. So B is a root node. And coming to this one, F, J, G, C. C is a root node because C is the last element. So in this post order, C is the last element. So C will be the root node. Now next, again based upon the root node, we have to find the left and right childs with the help of in order. Coming to this one, B here. So 3 elements are on the left child, 1 element is on the right child. So what are the 3 elements? H, D and I. And what is the left element? The right element? E. Only 1 element is there. Right. Coming to the F, C, J, G. C is a root node. So F, J, G. C is the root node. F is a left child. Only 1 child. And coming to this right, again there are 2 children, J and G. And we are supposed to find which one is the left, which one is the root here. See, in the HDI, again we have to find the root. So in order to find the root, go with the post order. So go with the post order, HDI, HID. So last element is the root. So HID, last D is the root. Okay. So based upon the root node, we have to find the left and right childs. It can be H and I. So D here. H is on the left side, I is on the right side. So H, I. Okay. Now J and G. J and G. So in that we have to find the root node. So in order to find the root node, go with the post order. So go with the post order J and G. So these two, J and G. Last element will be the root node. Last element will be the root node. So G is a root node. G is the root node. Okay. Now we have to find the left child and right child. So here only one thing. It can be either left child or right child. So that can be done with the help of in order. So J and G. So what is the root node here? G. So G is the root node. G is a root node. So J is to the left of G. So that means J is a left child of G. Right? This one. So hope you understood this one. So this is how we can construct a tree with the help of in order and the post order traversals. So in the post order traversal, the last one will be the root. So we will get the root node, and in order to find the left and left and right childs, we have to go with the in order traversal. With the help of the in order traversal, we can find the elements of a left subtree and elements of a right subtree, and just we'll repeat the same process and we can construct the binary tree. In this session, we'll go with one more topic, that is a binary search tree. Right. This is called as a BST, binary search tree. Right. So here it is also a tree. It is also a tree, and it should follow the condition of a binary tree. So we know the difference between a tree and a binary tree. So a tree consists of, in the tree, a normal tree, any node can have a number of children, but whereas in a binary tree, every node should have at most 2 children. So that constraint should be followed by BST. So here also every node should have at most 2 children. That means it is a variant of a binary tree. It is a variant of a
So we can call it as a type. Okay. So every node must have at most, so this is very important, 0, 1 or 2. At most means at most 2 children, right? So that's why we call it as a variant of a binary tree. That's the one thing. Second one is this is almost similar to our binary search. So just recall the binary search. So let us take an elements. See, so only one condition while implementing this binary search means, so before going to the binary search, the elements should be in a sorted order. So if they are not in sorted order, first we have to sort them and then we have to apply the binary search. So if let us take these elements, and what is the first step we are going to see in the binary search? So this is a binary search. Okay. Right. So first we will find the middle element. We will find the middle element, so that all the elements which are left to that are less than middle element. All the elements which are on the right side, those are greater than middle element. Right. Again, recursively we will find the same middle element in the left part, and the same middle element in the right part, and based upon the middle element we will just reduce the problem space. So like this we will apply this binary search. The same thing will apply in the binary search tree also. So here in this binary search tree, this middle element will be considered as a root node, right? This middle element will be considered as a root node, and this will be considered as a left subtree, and this will be considered as a right subtree. Right? So again, recursively in this left subtree we will find the middle element that will be considered as a root, and the left side is a left subtree, right side is a right subtree. Similarly, in this right part we will again find the middle element. We will consider that element as a root, and the left part will be the left subtree and the right part will be the right subtree. Recursively we will call that, right? So the same thing will apply for the tree construction. So that's why we can say, by using this binary search plus binary tree, we can form the BST, right? See, so binary tree plus binary search is nothing but our BST, binary search tree, right? So see, that means all the elements of left subtree are less than root. All the elements of a left subtree must be less than a root node. Similarly, all the elements of right subtree must be greater than root. All the elements of right subtree must be greater than root. All the elements of left subtree must be greater than root, right? See, if you consider some 50, let it be a 50 is a root node. So the left subtree should contain the less than 50 and the right subtree should contain greater than 50. See, 40, 60, right? So this is a BST because a node 50 is having less than on left side, greater than on right side. Next, if you form this subtree, again if you want to add a children to this 40, again we have to follow the same thing. So for the 40, the left subtree of this 40 should be less than 40 and the right subtree of this 40 should be greater than 40, but not less than, but not greater than 50. See here, if you observe, this is a root node now. This is a root node. So here we can apply 30 because 30 is less than 40. And here that should be greater than 40, right? Greater than 40. So if you place a 70, that is completely wrong because all the elements of left subtree, so this is all the subtree, right? This is all the subtree. All the elements of left subtree must be less than root. Here root is 50, right? Here root is 50. So 40 is less than 50, correct? So 40 is a root. 30 is less than 40, right? 70 is greater than 40. The condition is true, but the 70 is greater than 50, which is a root of this subtree. So we can't insert this 70 here, right? The condition is here we can insert the element which is greater than the 40 but less than 50. So we can insert a 45 here. So hope you understood. This is completely left subtree. So we know that all the elements of the left subtree must be less than root. So we can't insert an element which is greater than the root element. Next, here also we can write. So here we can write a 20 and here if you write some 42, that is completely wrong because 40 is the root here. So all the elements of a subtree. So this is a subtree of 40. This is a subtree of 40. So all the elements of subtree must be less than root. So all the elements of this subtree should be less than 40. So on the right side of this 30, it should be greater element but less than this root. So 40 will be not accepted here. So here we can insert a 35. We can insert a 35. Here also same thing. So 60. So if you insert a 20, so the 20 is less than 60. Condition is true, but 20 is less than 50 also. But so this is the subtree of right subtree of node 50. So all the elements of this subtree should be greater than 50. And if you write if 60 here, you have to insert 55. We can insert a 55 which is greater than 50 and less than 60. And here you can go with the 70. Right? So hope you understood this thing. So every element of a left subtree must be less than the root. So every iteration or every subtree we have to follow these two things. So all the elements of left subtree must be less than root. All the elements of right subtree must be greater than root. Right? So this is how we will follow while constructing the binary search tree. Right? So hope you understood without any problem. Right? Next. So what are the operations that we can apply on this BST? So operations. So we know that first one is insertion, inserting an element into the binary by a BST. So how to insert an element? So just by comparing the root element, we can insert an element into the BST because we know that all the elements are in a sorted order. That means
based upon the root node, we can find the position of the element while inserting an element. So if the node is, if the element is greater than the root, then automatically the position of that particular element will be on the right side, right subtree. If the new element is less than the root node, then the position of that particular new element will be on the left subtree. And coming to the left subtree, again repeat the same process. So by that way we can insert an element into the binary search tree. Next, deletion. So how to delete an element from the binary search tree? So here we will go with the three concepts. So deleting an element or deleting a node with 0 children, 1 children and 2 children, right? So we can how to delete an element with 0 children, that means a leaf nodes. So there will be no problem while deleting a leaf nodes, right? So how to delete an element with 1 child and the 2 child, right? Because our BST is a variant of binary tree, so every node may have at most at most 2 children. So this is a deletion process. So we'll go one by one, right? Third, searching process. So searching the element in the BST. So we'll find whether the element is available in this BST or not. So just simply comparing the root nodes. So every process will be related to the root node. Similarly, minimum value. So how to find the minimum element from the BST, binary search tree. Maximum node. So finding the maximum element from the BST, right? So these are the operations we are going to see in the further sessions regarding this binary search tree. Binary search tree. So first one is insertion. So how to insert an element into the binary search tree. So based upon the root element, we'll go with the insertion. So here, as we have discussed in the previous session, all the elements, first we have to set the root, and all the elements which are less than that root will be inserted to the left subtree, and what are the elements that are greater than the root are inserted in the right subtree. The same thing will follow. First step, so if tree is empty, then consider the element as a root. If the element is greater than root, insert to right subtree. If the element is less than root, insert to left subtree. So only 3 steps. So first we will find whether the tree is empty or not. If tree is empty, set that element as a root element. And for the next insertion, if the element is greater than the root, the position will be on right subtree. And if the element is less than the root, the position will be on left subtree. And we have to follow the same procedure for right subtree and left subtree. So while insertion to right subtree, follow the same procedure. While insertion to left subtree, follows the same procedure. So first find out whether the left subtree is empty or not. If left subtree is empty, then that element will be coming the root of the left subtree. So hope you understood. And if the element is greater than the root of left subtree, then that element should be inserted towards the right subtree of the left subtree. Right? Right. So same process, the same 3 steps we are supposed to follow while inserting any element into the binary search tree. Right. So we'll go with the example so that you will be understood. See. So we'll take an element and we'll construct a binary search tree. So let us construct these elements. So now we will find the binary search tree. Now read the element, and what is the first step? First we have to check whether the tree is empty or not. If it is empty, consider that element as a root node. So 40, I'm taking the 40. So here there is no tree, so tree is empty. 40 will be considered as root node. So now 40 is a root node. Right. Next, coming to 30. Tree is empty. No, false. Go to the second step. 30 is greater than 40. False. 30 is less than 40. So 30 will be placed at left subtree. Position of 30 will be in the towards the left subtree. So in that left subtree, again we have to follow the same procedure. So again in this left subtree, tree is empty. So consider this as a root element. Consider this as a root element. Yes. Coming to 20. Again, tree is there with the 2 nodes. So 20 is not a root node. 20 is compared with the root node. 20 is less than 40. So the position of 20 will be on left subtree. So in that left subtree, again 20 is compared with 30 because 30 is a root in the left subtree. So 20 is compared with the 30. So 20 is less than 30. So go with the left part of the subtree. So again left part of the subtree is no element. So consider this element and insert that element at that position. Right. Coming to 50. 50. So tree is not empty. 50 is compared with the 40. So 50 is greater than 40. So 50, the position of 50 will be on right side of the root node. So right subtree of root node is empty. So consider this as a root node and insert it. 50. Right? Coming to 60. So here 60, here tree is not empty. 60 is greater than 40. So 60 belongs to right subtree. So in the right subtree, the root is fixed. In the right subtree, root is fixed. 50. So 60 is compared to the 50. So 60 is compared to the 50. 60 is greater than 50. So 60 should be placed right side towards the 50 because it is a greater than root node. The position of 60 must be at the right subtree. Hope you understood this one. Okay. Next 70. Tree is not empty. 70 is greater than 40. So it will go with the subtree, right subtree. Again in the right subtree, 70 is greater than 50. 50 is a root node. Right? So 70, the position of 70 should be on right hand side of this 50. So right hand side of the 50, again there is a one more element called 60. Again compare this 70 with 60. So again 70 is greater than 60. So 70 should be placed at the right side of this 60. So here the right side means right subtree. Okay, right subtree. 10. So here the tree is not empty. 10 is compared with the 40. 10 is less than 40. So it should be placed in left subtree. Coming to the second root, 30. 10 is less than 30. So 10, the position of 10 will be left side of this 30. Right? Next, again there is an element towards the 30 left, that is 20. So again 10 is compared with the 20. So 10 is less than 20. So 10 should be placed towards left to 20. Because left side the elements are less, less elements, right side it should be greater than root. So next 80. So 80 is compared with the 40, greater than 50. So next root, it will move to the next root. 80 is compared with the 50. So greater than, again it moves to the next root. 80 is greater than 60. True. Move to the left side root. So 80 is greater than 70. True. So this one, it will be inserted here. So this is the binary search tree for the given elements. See, there are no right elements in the left subtree and there are no left elements in the right subtree. Okay. Right. So hope you understood this one. So just comparing the element with the root node, we have to insert that element whether it in towards the right position or towards the left position. Right. So we'll take one more example. See, let us take this example. First, 50 is a root node. 30, which is a less than 30, it's a left subtree. 10 is less than 50. So 30, here we can write it 10. Then 60, which is a greater than 50, here we can insert the 60. 80, which is greater than 60, here we can insert 80. And 20 means, see, 50, 30. 20 is less than 30 and we'll move with this one. 20 is less than, 20 is greater than 10. So if it is greater than 10, it should be on right side. So here, it should be here. Okay. Next, if you place 70, so 70 is greater than 50. So it should be towards right subtree. So coming to the 60, 70 is a greater than 60. So right subtree. 70 is less than 80. So here we have to insert this 70. Right? If you insert a 55 element, so 55 is greater than 50, so it should be in right subtree. And 55 is less than 60, so it should be inserted here. Right? So hope you understood this one. And if you insert 35, so 50 is a root node, so 35 is less than 50, should be placed in left subtree, and 35 is greater than 30, it should be placed in right subtree, 35. And if you simply insert a element 5, so 5 is less than 50, so we have to insert this 5 towards the left subtree. So 5 is less than 30, left subtree. 5 is less than 10, left subtree. Right. Here we have to insert. Right. So like this, we can construct a binary search tree by the given elements. So this is nothing but an insertion. So how to insert an element into a binary search tree? So just comparing the root node. So recursively comparing the root node. So rather than comparing the root node, we can call it as recursively calling the root nodes. We can find the position of the element where to be inserted. Right? So hope you understood this one. So let us move with the one more example and we'll wind up. Okay. Right, we'll go with this example. So these are the elements. Now let us find. So 10 is a root element, right? 5, which is less than 10, so it should be placed at a left subtree. And 15, which is a greater than, so it should be placed at right subtree. 2 is less than 10, so it should be placed in left subtree. And in the left subtree again there is a root node, that is a 5. So 2 is less than 5, so it should be again placed towards the right or left of the 5. And coming to the 8, which is less than 10 and a greater than 5. So here we have to insert this 8. 13, which is a greater than 10 and a less than 15. So here there is a one more root, that is a 15, which is less than that 15. So it should be towards the left position, right? Next 19, which is a greater than 15. 6, which is less than 10 and greater than 5 and less than 8. So here we have to insert it, right? So this is how we can insert an elements into a binary search tree. If you observe here, so our condition is consider the root node and all the elements of the left subtree should be less than the root node. See, if you consider this one, so this is the left subtree. This is the left subtree. So all the elements of this left subtree are less than 10. The condition is true. And all the elements of right subtree should be greater than 10. Yes, correct. And coming to this node, so this is the left subtree and this is the right subtree. So all the elements of left subtree are less than root node. So that means a 5. So 2 is less than 5. All the elements of right subtree should be greater than the root node. So 8 and 6 greater than this one. Coming to this subtree, the left subtree must be less than root node. So 6 is less than 8. So the condition is satisfied here. Coming to this one, all the elements of right subtree are greater than root node. So 15, 13, 19 are greater than root node. Coming to this one, this is a left subtree. So left subtree 13 is less than 15, right? And this is only one element. So 19 is greater than 15. So this is how it satisfies the binary search tree. So first we have to fix the root node, and based upon the root node we will find the position of the element where we have to insert. If it is a less than, then it should be inserted towards the left subtree, and if it is a greater than, it should be inserted towards its right subtree. And we have to follow the same procedure for inserting an element into the left subtree and inserting an element into the right subtree. So in this session we'll go with the one more operation, that is deletion. So how to delete an element from the binary search tree and what is the procedure. Deletion in BST. BST is binary search tree. So just recall the property of binary search tree. So it is a variant of binary tree. That means every node should have at most 2 children, and also consider the root node, and all the elements which are less than the root node should be in the left subtree, and all the elements which are greater than the root node must be in the right subtree. And this should be followed in this also. So while deleting an element from the binary search tree, it should not violate the property of BST. So even though you delete the element from the binary search tree, the elements less than the root node should be in the left subtree, and the elements greater than a root node should be in the right subtree. See. So here we can delete an element in 3 cases. So first case, deleting an element or deleting a node
no children. So we know that it's a variant of binary tree. Every node will be having at most two children. At most two children means we can have a 0, 1 or 2. Every node will be having either 0, 1 or 2 children. So deleting a node with no children, deleting a node having one child deleting a node having two children. Right. So these are the three cases we can follow while deleting an element from the BST. So here element or node both are equal, right? So let us see one by one. So we have to delete an element from the BST so that the tree should not violate the property of BST. Let us consider the first thing. Deleting a node having no children. That means leaf nodes. Leaf nodes. So let us take an example. So there will be no problem if you delete the elements of a leaf node, right? So that the property will not violate the BST, right? So let us take an example so that you will be understand, right? Right. So let us take this example so that first we will construct the binary search tree and then we will delete the leaf elements. So first consider the root node. Then 3 is less than 8, so it should be in the left subtree. 10 greater than, so right subtree. 1 less than, so again 1 is less than 3, so left subtree of 3. 6 less than 8 and greater than 3, so here it will be inserted. 14 greater than 8 and greater than 10, so right side. 4 less than 8 and greater than 3 and less than 6. 7 less than 8 greater than 3 greater than 6. 13, so greater than 8, right? So greater than 10, less than 14, right? So this one is a 14. This is the binary tree, okay, for these elements. Now delete the nodes which are having a no children, so that means leaf nodes. So here the leaf nodes are 1, so because it doesn't have any children, comma 13, only 2 elements are there, this one, this one. So deleting the elements or deleting the nodes with no children doesn't affect the BST. Just remove the connection between this element and parent element and just free this node. So after deleting the elements, we will get 8, 3, 10, 6, 4, 7, 14. That's it. Right? So after deleting one and 13, right? Just we have removed the connection between the leaf node and the parent node, right? And here let us check the property of BST. 8 is a root node, so that this subtree the complete left subtree should contain the elements which are less than 8. So 3 is less than 8, 6 is less than 8, 4, 7. All these are elements are less than 8. Right. Next, this is the right subtree. So we know that all the elements of a right subtree should contain a greater than the root node. So here 10, 14. Both elements are greater than 8. Right. So it satisfies the BST even though deleting the leaf nodes 1 and 13. So there is no issues. Simply we can remove the connection and we can free the node if it is a leaf node. So that is the first thing. We'll go with the second thing. So deleting a node having one children, that means one child. One child. Right? So let us take the same example. Same example. See, deleting a node having one child. So we have to delete a node which is having only one child. So here 8 is having 2 children, 3 is having 2 children, 6 is having 2 children, and coming to this 10 having only one children. 10 is having only one child. So single child nodes. What is that? 10, comma, and 14 is also having only one child. So 14. So we can delete the elements 10 and 14. So first let us delete the 10. First let us delete the 10. So simply if you delete the 10, the child will becomes the child will replace the position of the parent. So if the parent is having only one child, the child will replace the position of the parent. So here child will replace the position of a parent. Right? This is the only thing happens in deleting a node having one child. So after deleting an elements, let us check the property of a BST. Now we will delete the 10 element. Deleting 10. After deleting 10, see 8, 3, 1, 6, 4, 7. Right? Right. Then we are deleting the 10. So what is the child of a 10? It's a 14. Right? We are deleting the element 10. So what is the child of 14? So here the statement is child will replace the position of a parent. So 14 will replace the position of a 10. So 14 becomes the child of 8 because 10 is a child of 8. So 14, 13. So let us check whether it violates the property of BST. So this is the left subtree. So in the left subtree the elements are less than 8. So 3. So in this subtree again the elements of left subtree should have the less than root, that means less than 3, greater than 3. So 6, 4, 7 are greater than. And coming to the left subtree, greater than 8, so 14 and 13 are greater than 8. And coming to this 14, the 13 is less than 14, so 13 is a left subtree of 14. Right? So it doesn't violates the property of BST. It doesn't violates the property of BST even we deleting the element 10. So let us take 14. Let us delete the 14 from here. See, here we will write deleting 14, right? Because 14 is a node with only one child. So let us delete the 14. So if you observe here, the 14 is having the child 13. So from the statement, child will replace the position of a parent. So 13 will be the position of 14. 13 will be replaced with the position of 14. See, 8, 3, 1, 6, 4 and 7, and see 13 will be replaced to the position of 14. So 13, right? So after deleting the 14 from this one, okay, from this BST, after deleting the 10, we will get this one, this BST. From this BST, again if you delete the 14, we will get this one, right? So hope you understood. So again you can observe the property of BST. So it is also, it doesn't violate the property of BST even though we are deleting the 14. So this is how we can delete a node which is having only one child, right? Now two children. So how to delete a node having two children? Right. See here we can we have to modify a simple thing. So deleting a node with two children. So here also we can replace the parent position with another node, right? Another child. Here also we can replace parent with child. Okay, we can replace the parent with child. So in that, the child can be minimum element of right subtree or child can be maximum element of left subtree, right? Two cases we can replace. So here also if you are deleting a parent, right? So here we are deleting a parent which is having two children. So here we can replace a parent with a child. We can replace a parent with a child. One is from the left child, left subtree. One may be from the right subtree. So any one can consider. So if you consider the left subtree, the minimum, the maximum element from the left subtree should be replaced. And if you consider the minimum right subtree, the minimum element from the right subtree should be replaced. Any one should be happened, but not both. Okay, the parent can be replaced with the child either from left subtree or right subtree based upon this condition. Right. Now let us check here. Now so here what are the nodes which are having two children? Nodes with two children. So first one 8 is a root node, it's having two children. 3 is having two children. 6 is having two children. 8,
3, 6. Right. So 3 elements are there. We can delete 3 elements here in the third case. So let us consider one by one. So let us consider the 6. Let us consider the first 6. Let us delete the 6. So deleting the 6 should be replaced with a child from either left subtree or a right subtree. So if you consider the left subtree, the maximum element should be replaced. See. So here 8, 3, 10, 1, 6, 4, 7, 14, 13. See, if you observe here, so we are replacing this 6, right, with either left subtree or right subtree. So left subtree means maximum element. So here only 2 elements. We can replace either with 4 or 7. So if you replace the 4, we have to delete this element 4, right? After replacing, we have to delete this element. So deleting this element means this is a leaf node, so we can directly delete this, right? So this is one way how to delete a node. So the parent node will be replaced with the either left child or right child. So coming to the left child, we have to consider the maximum element, and coming to the right child, we have to consider the minimum element. So this we can apply, or you can go with the 7. That means replacing the child with the element from right subtree. So we can replace 6 with either 4 or 7. So even deleting the 6 also, the property of BST is not violated, because all the elements of the left subtree are less than 8, all the elements of right subtree are greater than 8. Right. So coming to the 3. So if you delete the element 3, see, deleting an element from, deleting the node 3. So the position of 3 can be replaced with the child of left subtree or right subtree. So here consider the left subtree. First case, consider the left subtree. So here it is a leaf node. It doesn't have any children, right? So it will be directly replaced with the 3. So one thing is, if you replace the 3, if you replace the parent 3 with the left node, that is 1, the tree is like this. This is also correct, right? So we can replace the parent with child from the left subtree or right subtree. If you consider left subtree, we have to go with the maximum element. So here the maximum element is only 1. One element is there. So we can replace the parent with that particular element. So 1 is here, and we can simply delete this node, leaf node. So 1, so the 6 is greater than 1, so it is on left side of the 1, right side of the 1, and 4, which is greater than 1 and less than 6. So 4 is also on the right subtree but left to 6, and 7, which is greater than 1 and 6, so 7 is placed at greater, so it should be placed at the right side, right subtree. So this also doesn't violate the property of binary search tree. So if you so second case, if you want to replace the parent from the right children, so right children means this one, right? From this right subtree, we have to replace the element. What is the maximum element of right subtree? 7. So minimum element of right subtree. What is the minimum element of this right subtree? 4. So 4 can be replaced with the, 3 can be replaced with the 4. So if you
replace this 3 with 4 and we have to simply delete this element. This is a normal, again this is a leaf node, so there will be no problem. And while deleting also we have to follow the same procedure, whether it is having a no children or 1 children or 2 children. So here 4 is having no children, it's a leaf node, so there is no change. So we can simply disconnect the link and we can free the space. So after deleting the 3, we are choosing the child from right subtree. So we are choosing the minimum value. So that is replaced with the parent, right? So this is also correct. It also doesn't violates the BST, right? So for the less than elements are on left, right, greater than elements are on right side. So hope you understood this one. Okay, right. Now right, so now let us delete an element 8. So if you want to delete an element 8, so that can be done from the left subtree or the right subtree. Right? Coming to the left subtree, we have to replace the element with the maximum value of left subtree. So what is the maximum of left subtree? 7. So 8 can be replaced with 7. So here 8 can be replaced with 7. So there are 2 nodes. So we have to remove this 7. So there should not be a duplicates. We have to delete the 7. Again, follow the same procedure. Check whether the 7 is a leaf node or a node with 1 child or node with 2 childs, and follow the same procedure. So here it is a leaf node. So simply we can remove the element. So it doesn't violate the property, BST property, because all the elements of left subtree are less than 7. So 3 is less than 7, 1 is less than 7 and less than 3, so it is a left subtree, and 6 which is less than 7 and greater than 3, and 4 which is less than 7 and greater than 3 and less than 6, right? So 10, 14 and 13. So it doesn't violate the BST property. So this is one way. So this is one way if you choose a child from left subtree, right? Now we'll go with the right subtree. So if you want to replace this position with the element from right subtree, so we have to find the minimum element. So what are the elements of right subtree? 10, 14 and 13. 10, 14 and 13. So among these 10, 14, 13, what is the minimum element? 10. So 10 should be replaced 10 should be replaced to position of 8. So if you replace this 8 with 10, we have to delete this 10 node, right? So in order to delete this 10 node, see, 10 is again, it's a node with 1 child. So node with 1 child means simply we can replace the position of a parent with a child, only 1 child. So we can replace the position of parent with that particular child. So 10 is replaced with 14. Again 14, we have to delete the 14. So 14 is not a leaf node. So 14 should be, again 14 is also a node with a single element. So 14 should be replaced with child. So here 13, right? And 13 is a leaf node. So simply we can remove the 13. So this is how we have to apply the deletion operation. So after deleting the element, so just deleting an element means replacing the parent position with a child. And after replacing the parent with child, and we have to remove that original position of that particular child.
and after also for removing that original position of the child we have to follow the same procedure, right? Don't get confused, and it was simple, easy, and hope you understood this one, right? So three ways we can delete an element from the BST. One is leaf nodes, a node with one child and node with two childs, research tree. So in this session we will go with the another operation, that is searching operation. Searching in binary search tree. So in the introduction we have discussed that binary search tree is a combination of binary tree and a binary search. So the searching is very easy in binary search tree, and which is very similar to our binary search. So in that binary search we will find the middle element, and based upon the middle element we are dividing the problem space, right? So if the key value is less than the middle element, then the search space is reduced so that we are searching the element in between 0 and mid -1. And if the search element is greater than the middle value, then we are reducing the search space and we are only searching in mid +1 to end element, right? So based upon the middle element we are reducing the search space in the binary search. So here the middle element is nothing but our root node. So coming to the property of binary tree, binary search tree, so all the elements of left subtree should be less than the root node, and all the elements of right subtree should be greater than the root node. So here in our searching process, this root node is a middle element, right? So based upon the root node we'll go with the searching, right? So if the key value is less than the middle element, that means if the key value is less than the root, then the search space will be on left subtree, and if the key value is greater than root, the search space will be on right subtree. So here the three steps. So first one, key is equal to root, automatically we will find the element. Second, key is less than root, so here the search space will be reduced. So search space will be in left subtree, right? So according to our BST property. The third case, key is greater than root. We know that all the elements of greater than root will be on right subtree. So the search space will be on right subtree. So this is implemented in a recursive way. Okay. So here, see, for this, if it satisfies key is equal to root, then we have to return, search is successful, right? So search is successful, that means element is found in the binary search tree. And if key is less than root, we have to again call the same process, but now the search space will be in the left subtree, right? So again we have to follow the same process. So recursive call, all these are implemented using a recursion. By recursively we can apply this searching technique, right? So let us take an example and then we will see the logic. So very simple.
Only three conditions: is equal to, greater than, and less than. If all these three conditions fails, that implies the element is not found in binary search tree. See, let us take a few elements. Example, let us take 50, 30, 70, 20, 40, 60 and 80. So these elements, first let us construct the binary search tree. So 50 is a root node, 30 is less than 50, so on the left hand side, 70 is greater than 50, so it's on right hand side, 20 is less than, so left hand side, and 20 is again less than 30, so left hand side, 40 which is greater than 30 and less than 50, 60 which is less than, greater than 50 and less than 70, 80 which is greater than 50 and greater than 70. Right? So this is the binary search tree for the given example. So we'll first represent this binary search tree in the list format. So list format, if you consider the list format, so we know that three fields will be there. The first one is data. The left hand side is the address of the next left subtree. Right hand side, right, again. Right. See, so this is 50, 30, 70, 20, 40, 60 and 80. Right. So this the address of this one is, let it be 1000. I will write here. So the address of this one is 1000. This is a 2000. This is the 3000. The address of this one is a 4000, 5000, 6000 and 7000. Let us assume that. So 50 left hand side, it address the 30. So what is the address of 30? 2000. So here we have to write it 2000. Here it is a 3000. So we have seen the representation of a tree, right? So here it will be the 4000, then 5000, 6000 and 7000. So here all these are the leaf nodes, right? All these are the leaf nodes. So all these are the leaf nodes, so it will be null. So all these are null because it doesn't points to any other element. Right. So all these are null. Now we have to search for an element. For search an element, we need a key value. So let it be a key is equal to some 40. Key is equal to 40. Right. So first, coming to the root node. So we have to check the three conditions: is equal to root, less than root and greater than root. So 40 is equal to 50, false. Now compare 40 and 50. So 40 is less than 50, so the 40 can be available on left subtree because all the elements which are less than root will be available in left subtree. So now we have to go with the left subtree. We have to reduce the search space to the left subtree. Again follow the same procedure. In the left subtree, what is the root? 30. Again key is compared with the 30. So 40 is equal to 30. False. So again compare. 40 is greater than 30. So all the elements which are greater than 30 will be available on its right subtree. So again the problem space is reduced to right subtree. So first left subtree, then right subtree. Again follow the same process. So key is equal to 40. Here the right subtree root is 40. Only one element is there. Fine. So automatically this 40 address will be returned. So here we are returning the address of the position. So just struct node start search so here we are taking two parameters, one is a root and another one is a key. Now here we can write the first condition, if root is equal to null, simply we need not go for the process, so just return a root, right? Else if the key value is equal to root of data, that implies the search element, the key element is found in the search tree. So we can simply return the root. Else if key value is less than root of data, we know that all the elements which are less than the key will be available in the left subtree. So we have to call recursively return search, again the same thing, search. Now the element will be root of left comma key, right? So hope you understood. First we are writing the root and key, two parameters. In the recursive call we are reducing the problem space or search space, so that root of left comma key. Else, so if both the conditions are failed, automatically we know that the key is greater than the root of data. So else we can return search of root of right comma key, right? Hope you understood this statement. So only three cases can be done for comparison of two variables. One is it may be equal, another one it may be less than, or another one it may be a greater than. So if these two condition fails, automatically it will the key value is greater than root of data. So if the key value is greater than root of data, we know that all the elements which are greater than root will be available on the right subtree. So we are simply writing here. So this is a code. So let us test once. So key is equal to 40. For let us take key is equal to 40. So key is equal to 40. First start node root. So here the root means the 1000 comma 40 will be passed as a parameters. So 1000 is the root. Now root is equal to null. So 1000 is equal to null. So that is false. 1000 is equal to null is a false. So else if key, so 40 is equal to root of data, so 50. It is also false. Now 40 is less than 50, true. 40 is less than 50, true. Now search root of left. What is the root of left? Root of left is 2000. So this is a 2000, this is a left and this is the right. So return search root of left, that means 2000 comma 40. Now the search space is limited to this left subtree, right? So just remove this. So after the first recursion, in the next recursion, the element are, the address is 2000 and the key value is a 40. Now again we have to proceed with the same process. So here 2000 is equal to null, false, right? So 40 is equal to 30, false. So 40 less than 30, false. So if all these condition fails, automatically search
So 40 is greater than 30 automatically. So root of right and key. Next iteration or next recursion, we have to go with the root of right and key. Here root is 30, root of right is 5000. So 5000 comma 40. Right? So in the second recursion, right? So here 5000 comma 40. Again repeat the same process. So 5000 is equal to null. 5000 is equal to null, false. So key 40 is equal to root of data, means root here 5000. 5000 of data is 40. So 40, true. So it returns the root. What is the root? 5000. So it will return 5000. So that means our element 40 is available at the position of 5000, at the address of 5000. Right? So hope you understood this example. Let us take one more example. That means we will change the key element which is not available in our binary search tree. Let us take a 10. Let us take 10. So we know that 10 is not available in our binary search tree. Now we will trace it. Right. So let us trace this one. First 10, key is equal to 10. So the root is obviously 1010. So 1000 is equal to null, false. So 10 is equal to 50 because root of data is 50, false. So 10 less than 50, true. 10 less than 50 is true. So search root of left means 2010. So now in the second recursion it will be 2010. So now repeat the same process. So 2000 is equal to null, false. So 10 is equal to 2000 of data. What is the 2000 of data? 30, false. Next 10 less than 30, true. So again the problem space is reduced, the search space is reduced to left of root. So what is the left of root? So root of left, here what is the root? Root is 2000, 2000 of left is a 4000. So 4000 comma 10. So in the next recursion the address is 4000 comma 10. So here 4010. So again the same process. 4000 is equal to null, false. 10 is equal to 4000 data. Excuse me. So 4000 of data means 20. So again it is a false. So 10 is less than 20, true. So again reduce the space. So root of left, here root is 4000. 4000 of left is a null because it is a leaf node. So it is a null, comma, key is 10. Right? So again recursive call, repeat the same. Here it is a null. Now null is equal to null, true. So automatically it will return the root. What is the root? It's nothing but a null. So if it returns null, it implies the data is not available in our binary search tree. So this is how we can apply the searching process in binary search tree. So just for understanding, I have represented this binary search tree in a linked list representation, double linked list. Right? So hope you understood this one. Let us stop here, and if you are having any doubts regarding the searching procedures, so this searching procedure is similar to our binary search algorithm. So there also we are checking the three conditions, whether is equal to, less than, or greater than, and recursively we are finding the middle element. So here also recursively we are finding the root element, and based upon the root we are checking the conditions. That's it. Right? Deletion and the search. Now we'll go with the another operations, that is finding the minimum element and finding the maximum element. So before going to that, let us recall the concept of binary search tree. So it's a one type of binary tree. That means every node must have an at most 2 children. That means every node should have either 0 or 1 or 2 children, and with a constraint, with separate a constraint, right? So what is the constraint? So all the elements which are less than the root should be available on the left subtree, and all the elements which are greater than the root should be available at right subtree. So that is a constraint for binary search tree. Now we'll go with the operations minimum and maximum. So finding minimum and maximum in binary search tree, right? So let us take an example. Right. So let us take an example, this one. So here it satisfies the property of binary search tree because all the elements are less than the root node on left subtree, and all the elements are greater than the root node on right subtree. Now our question is, we are supposed to find the maximum and minimum element, right? So first let us take the minimum element. Right. So minimum element. So according to the property of binary search tree, all the elements which are less than the root will be on left subtree. So this minimum element will be available on left subtree only. Left subtree. Right. So in this subtree itself it will be available, right? So again, calling the same function recursively, again consider this subtree as a tree, consider this as a node, and find the left subtree, right? Because the minimum element is available on left subtree. So keep on going with the root, right? First starting with the main root, so go with the subtree, and in the subtree again follow the root, and from the root again follow the subtree, right? So this is the recursive function. It's a recursive call. Recursively apply the same. So that means recursively we have to find the left subtree. So if the left subtree is null, then root will be the minimum element, right? See, for example, here there is no left subtree. Okay, so 50, 40, 45, 60, 55 and 65. So in this example, so all the elements are available which are less than the root will be on left subtree. So we have to follow this one. So we will follow the left subtree, that is 40 and 45. Again follow this subtree, so 40 and 45. So here what is the root? 40. So we have to find the elements which are less than 40, that will be available on left subtree. So here the left subtree is null. So then automatically the root will be the minimum element. So you can observe here 40 and 45. So left there are no elements. So 40 will be the minimum element, right? So we have to call this repeatedly. So I will write the function so that you will be understood. See. Struct node star, write in the function name. So let us call it as minimum BST. Pass an argument struct node star root. So we are considering root as an argument. So this is a function, recursive function. So if root node is equal to null, automatically the result will be the root. That means automatically the result will be the null. Else if we have to check one more condition. root of left, so we have to check this condition also. Root of left is equal to null. What is the result? Return root. So in the previous case I have shown, right? So in the absence of this node 30, so here the root is 40, there is no left subtree, so root of left will be null. That's why the result will be 40, right? Then else, so if root is not equal to null, if root of left is not equal to null, then what we have to do? Repeat the same process. So again consider the left subtree. So we have to repeat the same process recursively. So just pass this root of left as an argument to the function, recursive function. So return minimum of BST of root of left. So this ends the recursive function. So this is the recursive function for finding the minimum element. So if root is equal to null, then obviously we can stop that, because there is no node available in the root, so that's why it will return a root. So that means it will return an address, right? So else if root of left is equal to null, if a root of left is null, automatically the root will be the minimum element, right? If root is not equal to null, then we have to call the subtree. So if you observe this one, see, let us take 50 as a root, so root is equal to null, so not null, so root of left is equal to null, 40 not equal to null, so else minimum BST of root of left. So consider this subtree. So now the subtree is 40, 30 and 45. Again here the root is 45 now, sorry 40, the root is 40 now. Again follow the same procedure, root is null, not a null, root of left is null, no, then minimum BST root of left. So consider this left subtree, that means this one. Now the root will be 30 in the third recursion. So first recursion, second, third, right? Then root is equal to null, no, because here it's already a value is there, right? So this condition falls. If root of left is equal to null, so there is no left to this element, even though there is no right to this element. So we return root, so 30 will be the minimum element in this binary tree. So we can observe that in all these elements we know that 30 is the minimum element. So in such a way we can find the minimum element in binary search tree. In the binary search tree, now let us look with the maximum element, finding the maximum element. So let us recall the property of binary search tree, that all the elements which should be less than the root on the left subtree, and all the elements that are greater than the root should be on right subtree. So this is the constraint or a property of binary search tree, and now we'll find the maximum element in that binary search tree. So maximum in binary search tree. Right. So let us take an example. Let us take this example. So by observation we can say that 75 is the largest element in this binary search tree, right? Now let us find the procedure. So here our question is finding the maximum, right? So in order to find the maximum, we know that all the elements which are greater than the root node, that will be available on a right subtree. So this maximum element will be available on right subtree, right? And this should be called recursively. Recursively apply the same. So we have to apply the recursive procedure for finding the maximum element. That means finding the right subtree. In that right subtree, again find the root, and again find the right subtree to that root, and again in that subtree find the right subtree and find the root of the right subtree, and follow the same procedure until you get the maximum element. So we know that simply the rightmost leaf node will be the maximum element. Coming to the minimum element, the leftmost leaf node will be the minimum element, right? So we have to traverse such a way that finding out the right subtree. So let us write the recursive function. So similar to our minimum element, star struct node star maximum of BST struct node star root. So we are passing the root as a parameter. So same procedure, find out the condition root is equal to null. That means if 3 is empty, simply we can return null. That means simply root. Else if root of right, the rightmost element, is equal to null, then automatically the result will be the root element. See, if you observe here, in the absence of this 75, so first we will find the 60. So next we will find the right subtree. In that right subtree, again 70 is the root node. Again find the right subtree for this 70. So there is no right subtree for this 70. Sorry. Right. So there is no right subtree for this 70. So that means here 70 will be the maximum element, right? So the same thing, if root is equal to null, empty tree, the result will be null. If root of right is equal to null, then root will be the result. Else, that means if the root is having a right, then we have to again apply the recursive call. So apply the recursive, so return maximum BST of root of right. It's a simple thing. So in the next recursion, this 70 will be the root element. Right. Okay. So let us take an example here. First root will be the 60. So 60 is not equal to null and 60 of right is not equal to null. So these two conditions failed. So automatically we have to call this one. So that means, so if these two conditions fails, that implies the right of 60 is having a root, right? So the root of right is having a subtree, right subtree. So we have to call this recursion, right? So maximum BST of root of right. What is the root of right? 70 now. So in the second one recursion, it's a 70 now. So we are dividing this into the right subtree. So this will be here 70, 65 and 75, right? So here again root is not equal to null and root of right is equal to not equal to null, because here root of right is having a 75, element 75, right? So this is the root of right is 75. So root of right is also not equal to null. So this is also a failure condition. So again this recursion will be called. Now root of right is a parameter for maximum BST function. Root of right means 75. So in the next recursion, the root will be 75. Follow the same procedure. So root is equal to null because this fails. So this fails because root is equal to 75 now. Now else if root of right is equal to null. So there is no right children for this element. There is no right children or left children for this element. That means this condition is true. Root of right is equal to null. This condition is true. Then obviously return root. So it will return this 75. So this is the maximum element of given binary search tree. So by observation we can directly say that, so among all these elements 75 is the largest element, right? So this is how we can find the maximum element from the given binary search tree. Right? So this is also a type of binary tree, that means it's a type of binary tree that means it satisfies the property of a binary tree. That means every node should contain at most 2 children. That means every node in this tree should have at least a 0 or a 1 or a 2 childs, not more than 2 childs. Right? That's a property of binary tree. Or we can also say it as it's a variant of binary search tree. Binary search tree. So it should obey the property of binary search tree also. That means all the elements which are on the left subtree should be less than the root node, and all the elements of right subtree should be greater than the root node. So it should obey the property of binary search tree also. And this is a self-balancing binary search tree. Self-balancing binary search tree, self-balancing binary search tree, which was invented by Adelson, Welsky and Lindas. So these 3 persons invented this self-balancing binary tree, so that's why it was named as AVL tree, right? So what is this self-balancing? What is this self-balancing? So self-balancing means here the balancing of heights of left subtree and right subtree. So balancing heights of left and right subtrees, right? So balancing the left and right subtrees. So this is measured in terms of balancing factor. Balancing factor, right? So balancing factor. So what is this balancing factor and how to calculate this balancing factor? And if this tree obeys, this binary search tree obeys this balancing factor, then only we can call that as a AVL tree, right? So this balancing factor is nothing but height of left subtree minus height of right subtree, right? So that means the difference of height of left subtree and right subtree. So that gives the balancing factor, which can be either 0, 1 or minus 1. Either 0, 1 or minus 1. So that means we can say every node should satisfy this balancing factor. That means every node must have the balancing factor as either 0 or 1 or minus 1. Right? So hope you understood. This AVL tree should satisfy the binary search tree property. Along with that binary search tree property, it also satisfies this balancing factor. That means every node should contain the balancing factor either 0, 1 or minus 1. What is the 0, 1, minus 1? How to calculate this balancing factor? That is the difference between the height of left subtree and the right subtree. Right? So first of all, height. How to calculate the height? It's the longest path from leaf node to that node. So from where we are finding the height, So the leaf node to that node, the longest path, gives the height of a node. So height of a subtree minus the height of a right subtree. Then we'll see an example. So don't get confused. So it should satisfy the binary search tree property, right? It should satisfy the binary tree, and also it should satisfy the self-balancing. That means balancing factor. Every node should have the balancing factor either 0, 1 or -1. If any node is having other than these three values, either 0, 1 or -1, that implies that is not a AVL tree. That doesn't call it as a AVL tree, right? Now let us see an example and let us see how we will get a 0, 1 or a -1. Let us take an example for AVL tree. Let us take this example first. See, let us take this example first. So, if you consider this example, we know that this one is the left subtree and this one is the right subtree. Right? Now, balancing factor. What is the balancing factor? See, balancing factor, first binary search tree. So binary search tree means all the elements which are on the left subtree are less than the root node, all the elements which are on the right subtree are greater than the root node. So it satisfies the binary search tree. Then coming to this balancing factor, what is the balancing factor for 80? So that is nothing but height of left subtree minus height of right subtree. So what is the height of left subtree? 2 minus what is the height of right subtree? 1, which is equal to 1, which is equal to 1, right? So it is in either 0, 1 or -1. So it satisfies the condition of AVL tree. So this is called AVL tree, right? So if this left subtree is having a few more elements, 30 and some 45, and again it is having 20 and a 35. Now what is the result? So what is the left subtree of this 80? So 1, 2, 3, 4. Height is 4. 1, 2, 3 and 4. Height is 4. Right subtree 1. We will get 3, which is not equal to 0, 1 or -1. So this is not an AVL tree. Not an AVL tree. So because every node should have the balancing factor either 0, 1 or -1, which violates this condition. Right? So that's why this is not an AVL tree. See, according to the balancing factor, so we have to calculate this balancing factor for every node, right? So if this balancing factor is a -1, if this balancing factor is a -1, this tree is called as right heavy AVL tree, right heavy AVL tree, or heavy right AVL tree, or heavy right AVL tree, right? If it is a 0, it is called balancing AVL tree. it is 1, then we call it as heavy left ABL tree. It is called a heavy left ABL tree, right? So this is how we can consider so which type of ABL tree it is based upon the balancing factor, right? So we are supposed to find this balancing factor for every node of a binary search tree. If it satisfies, then we can call it as a binary search tree. So let us take this example. See, if you find the balancing factor for this one, height of left tree, that means 2 minus 1, which is 1. So what is 1? Heavy left or left heavy? Heavy left or left heavy? Left heavy tree, right? So heavy right or right heavy? Balanced tree. Right? So based upon this balancing factor value, we can have whether it is a left heavy or right heavy or a balanced tree. So this is, we are getting the balancing factor only 1, so we can call it as a left heavy balancing tree because the height of left is greater than the height of right. Height of left is greater than height of right. So if you avoid this one, if you consider this one 100, 90 and 110, see in this the balancing factor is height of left subtree. Height of left subtree means 1 minus height of right subtree 2, which is equal to minus 1. So it is within the given balancing factors. So if it is a minus 1, it is called as right heavy tree. Right heavy tree, because here we can observe that the height of left is less than height of right, or height of right is greater than height of left. So we will get the minus 1. So we can say it as a right heavy tree or heavy right tree. And if you have this one, see 40, 60. So if you consider this one, this also satisfies the binary search tree because all the elements on the left subtree are less than the root element, and all the elements which are greater than the root element are on right subtree. So it satisfies the binary search tree property. And coming to this balance factor, see if you observe this one, so balancing factor for every node you can check for every node, right? So here the right subtree height is 2 and left subtree height is 2, which is equal to 0. That means the height of left subtree is equal to height of right subtree. So if it is 0, then we call it as a balancing tree or a balanced tree, ABL tree, balanced ABL tree. So this is how we can find whether the given tree is a binary search tree or a ABL tree. So ABL tree is also one type of binary search tree with a balancing factor. So that's why we can call it as a ABL tree can be called as self-balancing binary search tree. And operations can be performed on this one. Those are insertion and deletion. So operations are insertion and deletion. So these two are the operations that can be performed on these ABL trees. So while after inserting or after deleting, that should not deviate this balancing factor. So that means if you insert an element into this ABL tree, that may disturb the property of ABL tree. That may disturb the balancing factor, right? So we have to take care while inserting an element so that the balancing factor should not change. That means the property of ABL tree should not violate. right? So that should be taken care while inserting an element or deleting an element from AVL tree, right? So we'll see these operations in the next session. So hope you understood this one. So AVL tree is also a variant of binary search tree that we call it as a self-balancing binary search tree. That means here we have to find the balancing factor, which is nothing but the height, the difference between the height of a left subtree and the right subtree. So the values may be -1, 0 or a 1. So if the height of left subtree is greater than height of right subtree, will get a value of 1, then that we call it as a left heavy tree. And if the height of right subtree is greater than height of left subtree, will get a -1, and we will call it as a right heavy tree. And if the height of right subtree and height of left subtree both are equal, then we'll get a 0 value, and that is called a balancing or a balanced AVL tree. So this is how we can find whether the given tree is a binary search tree or an AVL tree. So hope you understood this property of AVL tree, right? So we have to find this balancing factor for every node in the tree. So every node in the tree should satisfy this balancing factor. So that means every node in the tree should have either -1, 0 or 1 as a balancing factor.
And in today's session we will see the rotations involved in this AVL trees. Right, so there are two operations that can be performed on AVL trees. So before going to those operations, we will see the property of AVL tree. We will just recall the property of AVL tree. So AVL tree is a self-balancing binary search tree. So it should obey the property of binary search tree, as well as it should obey the balancing factors for every node. So here there will be a balancing factor which can be a value of either -1, 0 or 1. So we have to calculate this balancing factor for every node, and it should be one among these three values. So the balancing factor, the calculation of balancing factor is the height of left subtree minus height of right subtree. So for every node we have to calculate, and for every node the balancing factor should be either -1, 0 or 1. So that is the property of AVL tree. So in order to apply the operations, that means if you apply the insertion operation or a deletion operation, again if you insert any node, after inserting the node, again we have to calculate this balancing factor so that it should obey the property of both the binary search tree as well as the AVL tree. So it should not deviate from the property, right? So after insertion or deletion, right? So if it doesn't satisfy this AVL tree, I mean the property of AVL tree, that is called an imbalanced node. So that means if any node is having a balancing factor which is greater than 1 and less than -1, then that is called an imbalancing node. So for that imbalancing node, we have to balance the node by using a few rotations, right? So first we have to apply the insertion or deletion, and then again we have to check for the property of AVL tree. If it violates the property of AVL tree, we have to convert it as a balanced tree by using these rotations. See, there are mainly 4 rotations we can apply. The first one is if the node if the tree is like this, so now calculate the balancing factor for this every node for this tree. So for C, there are no left child and right child, so the balancing factor is 0. For B, there is a left child, so there is left subtree and there is no right subtree. So the height of left subtree is 1 and height of right subtree is 0, so that is equal to 1 minus 0, that is 1.
and here 2 minus 0, that is equal to 2. So here the node A, it violates the AVL tree property because the balancing factor for A is 2, which is not in a range of -1, 0 or 1. So here this is called, so why it became, because after inserting C to the left of left subtree. So inserting a node on left of left subtree. So that's why this rotation is called LL rotation. So this is called LL rotation, left of left rotation. Right? So hope you understood this one. Now we have to rotate towards the right. See, for this condition we have to rotate towards right. So in order to keep this tree as balanced, we have to rotate it towards the right. So after rotation towards the right, we'll get B as a root node, A as a left, C as a left, A as a right side. Okay, so here if you apply again the AVL tree, if you calculate the balancing factor for C, it is a 0 because the height, the leaf node, A is a leaf node, and B, the height of left subtree is 1, the height of right subtree is 1. So 1 minus 1, which is equal to 0. So that means the values are in between -1, 0 and 1. So that's why this tree is a balanced tree, and this is not a balanced, this is an imbalanced tree because the balancing factor of A is 2. So this is how we can apply for LL rotation, left rotation. Next, the second condition, second one, similarly right skewed. So previously we have seen the left skewed, now right skewed. Here also the same thing. So the value of the balancing factor of node C is 0. Balancing factor of node B is -1 because 0 minus 1, left tree minus right subtree. So -1. Here it is a -2. Again, the node A is having, it violates the AVL tree property. So here, how it becomes a right skew? Inserting a node on right of right subtree. That's why we call it as RR rotation. RR rotation. So in such case, we have to balance the tree by rotating on a left hand side. Rotating the tree on left hand side. So that's why after rotating we will get a B, A as a left child and C as a right child. So if you again apply the AVL tree, that means if you find the balancing factor for this one, it will be 0, 0 and obviously it will be 0. Right? So this is called RR rotation, right rotation. Next, if the situation is like this, A, B, C. So B is a left child for A, C is a right child for B. Now, what is the balancing factor for this one? It's a leaf node, so 0. For B, left is 0, right is 1, it will be -1. Next, right side, left side is 1 and 2,
right side is 0. So 2 minus 0, 2. So here again at node A it violates because node A is imbalanced, right? So now we have to balance it. So this can be done. So this happens when inserting a node on right of left subtree. Right of left subtree. Right? So this is called LR rotation. LR. Left subtree inserting a node at right. Left subtree inserting a node at right. So left subtree inserting node at right. Right? Don't get confused. So inserting a node on right of left subtree. So that is called LR. Left subtree on right side. Right. So this can be balanced in 2 steps. In 2 steps. So first step, see, consider this one. Right, where we have an imbalanced node, it is not at node A. So just ignore the root node, and from the next node you just rotate towards left. Rotate towards left. So after rotating towards left, what will be getting? So A, B, C. Right? So this is the result we get after rotating the subtree towards the left. Okay. So that is the first step. So now this is the left skewed. So always in the left right rotation, after applying the first step, we will get the left skewed tree. From the left skewed, in the step 2, what we have to do? So this is nothing but LL rotation. So after first step, we should not calculate the balancing factor, right? So this is a two-step process. LR rotation is a 2-step process. So after the first step, we have to consider, we will get the left skewed tree. So this left skewed tree should be balanced. So by using the LL rotation. So previously we have seen that LL rotation. So here we have to rotate towards left, including the root item. Including the root. So after rotation towards the right, we will get a C, B, A. So this is how we will get the result. So this one. So this is a condition where inserting a node on right side of left subtree. Right side of left subtree. Right? So that's why we call it as an LR rotation. Left subtree, right side. Left subtree, right side. So this process can be done. That means this imbalanced will be converted to the balanced in a 2-step process. 2-step process. So first step, other than the root node, rotate all the remaining nodes towards the left side. Right? So first apply the left, then apply the rotation. Simple logic. So first apply the left and second apply the rotation. So simple logic, first rotate all the nodes except the root node. So then obviously we will get the left skewed tree. And in the second step, this is a left skewed, we have seen the LL rotation. We have to apply the LL rotation. So once again I am saying that after the step 1 we should not calculate the balancing factor, because this is a 2-step process. We have to complete the 2 steps and then only we have to calculate the balancing factor. Right? So left skewed tree, so we have to apply the rotation in the second process. So first step left, second step right. So right side rotation. So we'll get this one.
So this is called LR rotation, right? So similarly, we have to go with the one more thing, that is see, there is a one more thing, A, B and C. So this is a next condition. So here we can see that the balancing factor for C is 0, for B is -1, for A is -2. Again, for at the node A it is imbalanced, right? So in such case, this is also a two-step process. So here why we got this imbalance? After inserting the element towards left of right subtree, left of right subtree. So this is called right subtree left side, right subtree left side. So this is called RL rotation. So here also the same process. It's a two-step process. After completion of the first step, we should not calculate the balancing factor. So A, B, C. So what is the first step? What operation we have to perform in the first step? We have to perform the right operation, right? So that means we have to rotate towards the right side. So accept the root node. Accept the root node. Accept the root node, we have to apply the right operation. I mean rotation operation towards right. Right. So after applying the right, we will get the right skewed tree. So one thing you have to remember, that always after the first step of RL rotation, we get the right skewed tree, and after the first step on LR rotation, we'll get the result as left subtree, right? Then so we got this one after the first step, and coming to the second step, see, consider this one, right? Consider this one. What we have to do in the second step, we have to apply the left rotation, including the root node, right? This we have to do. So after applying the left rotation, so this is nothing but RR rotation. So after applying this one, we'll get B, A as a left child, C as a right child. Now the balancing factor is 0 for all these things. So this is a balanced tree, right? So this is called a RL rotation. The first step, we have to rotate towards the right, except the root node, and the second step we'll get the right skewed tree. So we have to apply the RR rotation. RR rotation means we have to apply the left rotation, right? So this is how we can apply the rotations, and with the help of these rotations, we can have the imbalanced tree to the balanced tree after performing the insertion or a deletion. So that means after performing the insertion or a deletion, if there is any change in our AVL tree, that means if it violates the AVL tree property, then we have to apply these rotations and we have to reform the imbalanced tree to balanced tree, right? So see, rotations, first one is, we have seen LL rotation, which is a left skewed tree, and the second one we have seen RR rotation, which is right skewed tree. Third one, LR rotation. On the left tree, right side. And the fourth one is RL rotation. Right. This is the different rotations we have seen, and these two will come under single rotations. So that means we will perform only one rotation, single rotation, and this is a will perform double rotation. Double rotation, single rotation and a double rotation. So this is a two-step process. Two-step process. For the first step, we have to apply the we have to rotate towards the left, and the second step we have to rotate towards the right. Here in the first step we will rotate towards the right. Second step we will rotate towards left. Right. So in the LR, after the first step, we will get the left skewed tree. In the RL, we will get the result as right skewed tree. Right. So this is how we have to apply the rotations in order to change the imbalanced condition to balanced condition. Right. Right. Now let us see an example and let us construct an AVL tree for the given nodes. Right. Now let us see this example. Let us take these elements, and now we have to construct the AVL tree. That means inserting one element after another. And we have to take care, or we have to remember that after inserting an element, we have to check for the two properties. One is the binary search tree. That means all the left side nodes should be less than the root node, and all the right side nodes should be greater than the root node. That is the property we have to remember. And then we have to remember the second property, that is a AVL tree property. That is, for every node the balancing factor, that means for every node the height of the left subtree minus height of the right subtree must be either 1, -1 or 0. So two properties should be remembered, that is a BST property, second one is the AVL property. Right. So after first consider the 20. So first step, so 20 is a root node because empty. So here AVL tree is an empty. So 20 is a root node. Now second step, insert the 30. Insert 30. So after inserting that 30, so based upon the property of BST and AVL tree. So based upon the BST property, 30 is greater than 20. So 30 should be inserted on the right hand side of 20. Right. So this is the first one. Second one, AVL tree. AVL property. AVL property means this balancing factor should be either 1, 0 or -1. Right. So balancing factor. So balancing factor means height of left subtree minus height of right subtree. So here the height of left subtree, so there are no nodes, so 0, the height of left subtree is 0, height of right subtree for this 20, right, for this 20 there is only one node, so 0 minus 1, it is 1, the balancing factor is -1 for 20. For 30 it is a leaf node, so it is a leaf node, there will be no right children and left children, so that's why the balancing factor will be 0. So -1 and 0, so both are within the range. So this is also correct. It's balanced, right? It's a balanced. Third step, we have to insert the third element 80. So 80 is a greater than 20, so it should be inserted on right hand side. So in the right hand side again there is a 30. So in the 30 also 80 is greater than 30, so it should be inserted towards rightmost of this 30. So after inserting this one, the tree will be 30, 80. Right? So coming to the third one. So this is about the BST. This is a binary search tree. Now we have to go with the AVL property. AVL property means we have to find out the balancing factor. So from top, always calculate the balancing factor from bottom to top. So bottom to top, this is a leaf node. So the balancing factor will be 0. So this is a node with only one element, that is also rightmost element. So 0, left hand side there are no elements, right? So balancing factor is equal to 0 minus 1. This is minus 1. And again here also there are no left hand side elements, only the right hand side elements. What's the height of this node? Right subtree, height of right subtree is 2. Right? So height means the longest path from root node to, that node to leaf node. So 2. Here the balancing factor is 2. Left side balancing factor, left side height is 0. So 0 minus 2, it is minus 2. So which violates the AVL property, because for every node the balancing factor should be either minus 1, 0, 1. Here we got the 2. The balancing factor is 2. Right? So here this is an imbalanced tree. So this is an imbalanced tree. So what we have to do, in order to get this imbalance to balance, we have to use one among the 4 rotations. What are the 4 rotations? One is LL, RR, LR, RL. All these are the rotations. So based upon the situation we have to apply this one. So this is the right skewed. So when we got this imbalance, whenever we are inserting an element to the right subtree towards the rightmost element. So that means this is called RR rotation. So we have to apply the RR rotation. So after applying the RR rotation means we have to rotate this towards the left side. RR means towards left. So we have to rotate in this direction. So after rotating this one, we will get, so 30 will be moved here, 20 will be moved towards the left, 80 will be moved towards right. So after applying the RR rotation, we will get the result as this one. So here now we have to calculate the balancing factor. So these are the leaf nodes. The balancing factor will be 0, and this is the node. For this balancing factor is left side height minus right side height. Left side height is 1, right side height is 1. So 1 minus 1, it is again 0. So it obeys the property of AVL tree. Right. Now fourth element. So we have to insert the 40, element 40. So now the tree is like this: 30, towards the left there is a 20, towards the right there is a 80. Now we have to insert the element 40. So again that should obey the BST property. So 40 is greater than 30, so it should be inserted on right subtree. And again 80 is the root here, so 40 is less than 80. So here we have to insert the 40 as a left subtree for node 80. Now, so this satisfies the BST, because all the elements of right subtree are greater than root, all the elements of left subtree are less than root. This property is right. Now coming to the AVL property. So coming to the AVL property, we have to find out the balancing factor. So balancing factor for the leaf nodes is 0, and for this node 1 minus 0. So right subtree is 0, so 1 minus 0, 1, and for this one 1 minus 2, because the right subtree for this 30 is 2. The height of right subtree is 2, the height of left subtree is 1. So 1 minus 2, it is minus 1. So all the balancing factors are within the range, minus 1, 0 and 1. So it is a balance. Now coming to the fifth one. So we have to insert the element 10. So same property we have to use. So 30, 20, 80. So towards the left there is a 40 element 40. Now we have to insert the 10 element. So 10 is less than 30. So 10 should be inserted towards the left hand side, left subtree. In the left subtree there is a one root 20. So 10 is less than 20. 10 is less than 20. So 10 should be placed towards the left hand side. 10 should be placed towards the left hand side. Right? So now it obeys the BST because all the elements of left subtree are less than root element and all the elements of right subtree are greater than root element. Right? So now we will go with the AVL by calculating the balancing factors. So balancing factors of this one is 0 and this element is 1 minus 0 1, 1 minus 0 it's 1, this one 2 minus 2 0. Right? So again this is a balanced tree. Now sixth, that means we have to insert the element 60. So 30, 20, 80, 10, 40. Now we have to insert an element 60. So 60 is greater than 30, 60 is greater than root. So we have to insert the 60 towards the right side. So right side the root is 80. So 60 is again less than 80. So 60 should be towards the left hand side of left subtree of 80. Again left subtree we are having 40. So 60 is greater than 40. So 60 is greater than 40 means we have to insert this 60 here itself towards its right side. Towards it right side. Right? So here we are inserting. So again the DST property is satisfied because all the elements of right subtree are greater than root, all the elements of left subtree are less than root. This satisfies. Now calculate the AVL tree. Now calculate the property of AVL tree. So the leaf nodes, it will be 0 and for this one 0 minus 1 it's minus 1. For this one 2 minus 0 it's a 2. So just stop it. So we need not go with the remaining nodes. So here it violates the AVL tree. It violates the AVL tree. Right? So here we have to stop. So if you observe this one, when we got this imbalance, so this is a imbalance. This is the imbalance tree. Right? So in order to change this imbalance to balance, what we have to do? We have to apply one among these 4 rotations. So here when we are getting this violation, whenever we are inserting an element towards the right side, okay, and see, so here we have got the violation for 80, right? So left side, right side, okay, left and right. So you can observe this one. So this we got a violation. So this is the left node, right node, left node, right node. So that means LR rotation. We have to apply the LR rotation. So this is a 2-step process. So this is a 2-step process. So for the first step we have to apply the step 1. We have to rotate left side. So we have to rotate left side. Left side means see this way. So after applying this one, so let us erase this one. After applying this one, we'll get so 30, 20, 10, 80. Now after rotation 60 will become here. 60, 40. Right? So this is the first step. So after second step, so what we have to do? Second step, rotate right. Rotate right. So in this way we have to rotate. In this way we have to rotate. Right? So then it will becomes, so 30, 20, 10, 60, 40, 80. So this becomes this one, right? Now, so again, now we have to calculate the balancing factor. So here we should not calculate the balancing factor because this is a LR rotation. LR rotation means two-step process. So after completion of two steps only, we have to calculate the balancing factor. So these are the leaf nodes. The balancing factor will be 0, and for this node the balancing factor will be 0. For this node the balancing factor will be 1, and for this node the balancing factor will be 0, because height of left subtree is 2, height of right subtree is also 2. Now coming to the seventh one. So we have to insert 50 for this one. So 30, 20, 10, 60, 40, 80. So now we have to insert the 50, but it doesn't violate the BST. So if you insert a 50, so 50 is greater than 30, so it should be on the right subtree. 50 is less than 60, it should be on the left subtree, and 50 is greater than 40, it should be on right subtree. Now again calculate the balancing factor. So for the leaf nodes it's a 0, 0, 0. For this one, 0 minus 1, it's a minus 1. For this one, 2 minus 1, 1. For this one, 2 minus 3, it's a minus 1. So it satisfies, so it's a balanced tree, because for every node, for this one it's a 1. For this one it's a balanced tree, because for every node the balancing factor is either 1, 0 or minus 1. Now insertion of a, so 8, we have to insert the 70. So 30, 20, 10, 60, 40, 80, 50. Right? So this one. Now we have to insert the 70. That should not violate the BST. So 70 is greater than 30. So it should be inserted towards the right subtree. So in the right subtree 60 is there. So 70 is greater than 60. Again we have to go with the right subtree. In the right subtree there is a 80. So 70 is less than 80. So 70 should be placed here itself. So that means it should be placed towards the left hand side. For 40 it is a 50, and for 80 it is a 70. For 80 it is a 70. Right? So this is how we have to apply. Right? So here you can see the balancing factor. So for the leaf nodes the balancing factor is 0, and for this one it is 1, for this one minus 1, for this one 1, and for this one 2 minus 2, 0, for this one 2 minus 3, minus 1. So here it obeys the property of AVL tree. So that's why it is a balanced. So it obeys the BST property and it also obeys the AVL tree property. Right? So hope you understood this example. So don't get confused. So just we have to satisfy the BST property, binary search tree property. So based upon that binary search tree property, we have to insert the node into the AVL tree. That means the element should be compared with the root, and then we have to decide whether it should be inserted towards the left side or it should be inserted towards the right side. That's the first thing. So after insertion, second thing, we have to check for the balancing factor. So whether the tree is a balanced or not. So that's the definition of AVL trees, right? Self-balancing binary search tree. So for that balancing factor, we have to calculate the height of a left subtree minus height of the right subtree. So if that balancing factor is other than minus 1 or 0 or 1, that tree is an imbalanced tree. So for changing that imbalanced tree to balanced tree, we have to choose one among the 4 rotations. So LL rotation, RR rotation, LR rotation, RL rotation. Right? So based upon that thing, so here LR rotation and RL rotation are two-step process. So in the LR rotation, first we have to apply the left rotation, and then we have to, in the second step, we have to apply the right rotation. Coming to the RL, first we have to apply the right rotation, in the second step we have to apply the left rotation. Right? So this is how we have to insert an elements into the AVL tree. So this is simply, we call it as a construction of an AVL tree. Right? So the same process we have to apply while deleting an element from the AVL tree. So after deleting the element, again we have to check for the BST. The same process we will follow, which we have followed in the BST. So deleting an element from the binary search tree, the same process we will follow, but here addition to that we have to calculate the balancing factor, and based upon the balancing factor we have to apply the rotations to make the imbalance to balance. Right? So this is a simple example. So hope you understood this one. So here only two rotations are there, one is a RR and another one is LR. Right? So if you take one more example, then you may get a multiple number of rotations. Right? So graphs in a data structure is also similar to a trace, but here we can have a closed loop. Right? So whereas in a tree we can't go with a closed loop, but here graph can have a closed loop, and here the graph is defined as a set of V comma E pairs, where V is a set of vertices, E is a set of edges. So a graph can be defined as a set of vertices and a set of edges. So every graph will be having a vertices and a edges. So vertices can be represented as circles, and these are also known as nodes. Edge is represented as lines, and also so lines which are connecting two vertices or nodes. Two vertices or nodes. So a graph can be defined as vertices and edges. So vertices are represented as circles and the edge is represented in the lines. So let us take an example for this graph. This is a simple graph. This can be called as a graph. So here B and C are vertices or nodes, and the connectivity between the vertices AB and AC are, so AB, A comma B, A comma C. These are called edges. So edges means the connecting two nodes. Right? So this can be considered as a graph. And if you have a line between this B and C, so BC is also forms a pair, that means it is also an edge. So this is also a graph but not a tree. So in the absence of this one, in the absence of this edge, this can be either a graph or a tree, right? So if you have an edge between B and C, it is a closed loop, it's a closed surface, right? It forms a cycle. So if it forms a cycle, it cannot be called as a tree, it is a graph. That's the only difference between the tree and a graph. right? So here the nodes and edges. So let us see, first let us see the terminology of a graph, and then we will go with the types of graphs, different kinds of graphs. Graph terminology. The first one is node. First one is a node, which is nothing but vertices represented as a circle, and then edge, which is a line. It's a connection between two different nodes, right? The third one is adjacent nodes. Adjacent nodes. So if you consider any edge, that means there will be, so let us take an example, A, B, and similarly A, C, similarly B, C. So there are three edges, right? Three edges. So for this edge, the node A and B are the starting and ending points. For this edge, the node B is the starting point, C is the ending point. For this edge, A and C are the end points for this particular edge. So that's why the adjacent nodes means which connects an edge, those nodes we call it as adjacent nodes. In this example, A and B are adjacent nodes. Similarly, A and C are adjacent nodes. Similarly, B and C are adjacent nodes. So this is how we can have the edge. So degree of a node. So how to calculate a degree of a node? So it represents the number of edges corresponding to that particular node can be considered as a degree of node. Number of edges connected to that node. For example, let us take this one, A, B and C, right? Now degree of A, what is the degree of A? So A is having two nodes, so degree of A is 2. So degree of B is also having two nodes, so degree of B is 2. Similarly, degree of C is also having two nodes, 2. So in the absence of this one, so degree of A is 2, degree of B is 1, degree of C is 1, because B is having only one node towards A, C is also having one node towards A. So that's why we call this degree as the number of edges connected to that node. Size of a graph. Size of a graph. So size of a graph represents the total number of edges. The total number of edges in graph can be considered as the size of a graph. So let us take this example. So there are 3 edges in this graph. So size of this graph is 3. So size is 3. What about this example? Only 2 edges are there. So the size for this graph is 2. So the total number of edges in the graph represents the size of a graph. Path. Path means the sequence of vertices, so from starting node to ending node. So sequence of vertices. From source node to destination node. Source node to the destination node, right? So let us take an example here. So if you take this one, A, B, C, D. So if you want the path from A to C, right? A to C, so this is the source, this is the destination, the path will be A to B to C or A to D to C. So whatever the edges or the sequence of vertices from source node to destination node. So here the source is A and the destination is C. So we can have that the path can be A to B, B to C or A to D, D to C. Right? So this is called a path. Okay. Then, so these are the basic terminologies we need to know before starting the graphs concept. So hope you understood the definition of the graph. So graph is a set of vertices and edges. Right? Now we'll go with the different kinds of graphs, different types of graphs. Types of graphs. So the first one directed graph and undirected graph. Right. Directed and undirected. See, coming to this undirected, so there will be no directions specified on the edges. So let us take an example. So A, B, C, D and A. Let us take one more thing. So this one. Right. So this is also a graph. It contains vertices and edges. Right. So in this example, there is no directions specified on the edges. So we can travel from A to B or B to A. So here A comma B is equal to B comma A. Right. Similarly, B comma C is equal to C comma A. So that means there is no direction specified in this graph. So we can consider that A and B, A to B is one traversal and B to A is another traversal. So in both the directions we can travel, right? In both the directions we can travel. So coming to the directed graph, as the name indicates, so every edge will be having a specific direction. That means, so this we can call as a bidirectional, right? This we can call as a unidirectional. So in only one direction we can travel through the edges, right? See, let us take an example here. A, B, C, D, A. So this is called a directed graph because so here every edge is specified some direction. So only one direction we can travel. So there is a node between A and B. So A and B is not equal to B comma A because here we have specified the direction from A to B, not from B to A. So here B to C. So direction is only from B to C. So B is the starting point and C is the ending point, but not the vice versa, right? So this is the only difference between the directed graph and undirected graph, right? So hope you understood. It's a bidirectional, it's a unidirectional. It's a bidirectional, it's a unidirectional. So only one way we can travel. So this is the difference between directed graph and undirected graph. Now we'll go with the another kind, right? Weighted graph unweighted graph, weighted and unweighted. So here we have to specify some weight or a cost for the edge. See, let it be either it may be a directed graph or undirected graph. So there is no any cost specified for that edge. So here we can specify some cost for every edge. So in order to travel from A to B, the cost is 2. That means here we are specifying some weightage for every edge. So if you specify some weightage for every edge, that is called a weighted graph. So here weight is specified for every edge. No weight is specified. So either it may be a directed or undirected, whatever it may be. So in the directed also we can have the weighted, and in the undirected also we can have the unweighted, right? So whatever it may be, if the edge is having any weight or a cost, then that graph is called as a weighted graph. And if the graph doesn't have any cost or weight specified for the edge, that is called unweighted graph. So this is a difference between weighted graph and unweighted graph, right? Now we'll go with the third one. Cyclic graph and acyclic graph. Cyclic and acyclic. So cyclic means it should perform the loops. Loop means, so if you find the path from source to destination, the starting point and the ending point should be the same vertices. I will show the example. So if you consider this one, find the path here. So here you can form, so A to B, B to C, C to D, and again D to A. So the starting vertex and the end vertex both are same. So that means it forms a cycle. It forms a cycle, right? So hope you understood this one. So if the starting vertex and the ending vertex are same, then that forms a cycle. And if our graph consists of the cycles, then it is called a cyclic graph. If our graph doesn't have a cycle, then that is called a cyclic graph. See, so here it doesn't form any cycle. It doesn't form any cycle. So this is called a cyclic graph. So similarly we can say this one. So if any graph doesn't have the loops, that we can call as a acyclic. So in the acyclic also, this graph can be either directed or undirected. It can be weighted or unweighted. So whatever it may be, if our graph consists of the cycles, then we call it as a cyclic. If it doesn't have any cycles, it is called as acyclic graph. Right? So hope you understood this one. So weighted, unweighted, directed, undirected, cyclic and acyclic. So these are the different kinds of graphs available in our data structure. Right? And also we have seen a few terminologies. So what is meant by an edge, what is meant by a graph, and what is meant by a node, what is meant by path, and degree, how to find the degree, how to find the size, and everything we have seen in this session. Now in this session we'll go with the one more concept, that is how to represent a graph. So representation of graphs. So a graph can be represented in two ways. So first one is using multi-dimensional array another one using list concept. Using linked list, right? So we'll see how a graph can be represented by using multi-dimensional array and how a graph can be represented by using the list. First, we'll go with the multi-dimensional array. So let us take an example for this graph and then we'll apply the representation. We'll see the representation. So we will take the similar example which we have considered in the previous session. So this is a graph. Let us take this is a graph and we have to represent this in a multi-dimensional array. So here we have to represent in two-dimensional. So these are the nodes and these are the nodes again. So rows and columns represents the nodes, and now we have to fill this multi-dimensional array with zeros and ones. So if an edge between the two vertices is available, then that will be filled with 1, otherwise it will be filled with 0. Now A and A, so A and A, there is no edge. So there is a possibility to have an edge between A and A, right? There is a self loop. Self loop is also available in a graph, right? So A can have a self loop. So in this example, we doesn't have any self loop. So A doesn't have a node from A to A. So filled with 0. A to B, yes, it is having an edge. So 1. A to C, there is no edge. 0. A to D, yes, 1. Similarly, B to A, yes. So this is a undirected graph. So it's a bidirectional. So A and B is equal to B and A, right? So similarly, B can also have an edge from B to A. So B to A, 1. So B to B, there is no self loop. B to C, there is a edge. B to D, there is no edge. Similarly, C to A, no edge. C to B, there is a 1 edge. C to D, so C to C, no loop. C to D, 1 edge. D to A, 1 edge. D to B, 0. D to C, 1 edge. And D to D, there is no self. Right? So this is how we can represent a graph in adjacency matrix. That means a multi-dimensional array. By using the multi-dimensional array, we can represent any graph here. So if the same example see, if it is having a directed graph, so this is a unidirectional. So let us see the matrix. See, A to A, no. A to B, there is 1 edge. A to C, 0 edge. A to D, yes, there is an edge. It's a unidirectional, right? So A to D is also 1. Similarly, B to A, 0, because here A to B is not equal to B to A, because there is a directed graph, directed edge, right? So the direction is towards A to B, not from B to A. So B to A is 0. So next B to B, 0. B to C, it's 1. B to D, it's again 0. Similarly, C to A, 0. C to B, again it's a unidirectional, and that edge is from B to C, not from C to B. C to C, it's again 0. C to D, 1. D to A, it's a unidirection, so it is 0. D to B, 0. D to C, 0. D to D, again it's 0. So this is a matrix represented for this directed graph. It's an undirected graph and this is a directed graph. right? So hope you understood this, how to represent a graph using a multidimensional array, right? Now we'll see the another type of representation by using list. This is also similar. We know that every node will be having two fields, one is the data field, another one is the address field. So for example, consider A. So A is having two nodes, one is from B, one to D. So we can represent like this. So B again points to D, right? So A can be having a nodes connectivity from B and D. Similarly, coming to the B is also having two nodes. So what are the two nodes here? B, A and C. So A connecting to C. So even though there is no connection, B is having two edges. The two edges can be represented in this similar way. And C is also having two nodes, B and D. So B and D, right? And D is also having, say, let us have this one. Okay, let us have this one. Now D is having three nodes, A, B and C. So I have to write all these things. So A, B, C. So in such a way we have to represent a graph using linked list. So this implies A is having a node to B and to D. B is also having an edge from A and to C. C is having an edge for B and D. D is also having an edge for A and B and C. Coming to this, so this is a null, right? This is a null, right? Coming to this one, coming to this directed graph. So how to represent A? A is having two nodes, B and D. B, D. And coming to the node B, B is having only one edge towards the C. C. C is having only edge for D. And D. D is having only one edge from D to B. So this is how we have to represent a graph, using linked list. So in some references you can find for A there is having B and D, and here B some having A and C, nodes A and C, and C is having some nodes B and D, and D is having nodes A, B, C. And similarly for this also you can observe A is having a link between B and D, and B is having a link to C, C is having a link to D, and D is having a link to D. So you can find in two ways. So in different ways we can represent the graph using list. So this is how we can represent any graph using multidimensional arrays by using the adjacency matrix and as well as the list concept, right? So hope you understood this session. In this session we'll go with another concept in graph, that is graph traversals. So our topic is graph traversals. So what is meant by this traversals? So traversal means visiting all the nodes. That means traveling around all the nodes in the graph. So here we will not have any root node, so we can assume any node as a starting node. Any node as a starting node. And from that starting node we have to visit all the nodes without any repetition. That means every node of a graph should be visited only once. Right? Now we are having two types of techniques in this traversal, graph traversals. So the first one is depth first search traversal. It is called as DFS, and the second one is breadth first search. Which is called a BFS, right? So based upon the depth, we will travel all the nodes of a graph, that is called a DFS. Based upon the breadth, that means level, so we have to visit all the nodes of a same level, then only we will shift to the next level. So that in such a way we will go with the BFS, we will implement this BFS. So in order to implement this DFS and BFS, we will use the stack data structure. For implementing the DFS, we will use queue data structure for implementing the BFS, right? So now let us take an example and we will see the procedure, how the DFS will work and how the BFS will work. It's a very simple topic, right? Now, coming to this DFS, see, let us take an example here, A, B, C, yes, so you can go with this one. Okay, so you can go with this one. This is a graph. So graph is also similar to a tree, but a graph can contain cycles, that means loops. So this is a graph, of course, alright. So now first let us assume this one is a start. So we can assume anything, any node can be a start. Okay, I will assume that a start for simple understanding. Right. So I will visit one by one. Okay. So after visiting this one, so I will place a weight as 1. I have visited A, I have placed it as 1. Now I am coming to C. Right. So you can go with the B or C, anything else. Okay, both are same. You can visit either B or C, so we can get a different outputs. Okay, so I will visit C, so the C weight is 1. Now from the C again there are two adjacent nodes, so we can visit any one node. Okay, so I will go with the G, and the weight of G is 1. Now it is a leaf node, there are no nodes. Okay, there are no adjacent nodes. We should not say it is a leaf node. We are not having any adjacent nodes. So backtrack C and go with another adjacent node, right? And mark it as 1. So here also there is no adjacent nodes. Again backtrack, so again the node is visited, so go with the adjacent node. So B will be 1. Now again B is having two adjacent nodes. We can go with the D or E, anything. Okay, so I will go with the D. Mark as D1. Again there are no adjacent nodes. Backtrack, right? Again go with the E and go with the 1. So there are no nodes. Okay, there are no adjacent nodes. Backtrack and again backtrack. Again we came to the start node and there are no adjacent nodes. So this is how we can use this DFS. So first we have visited A, then C, then G, again backtrack C. So already C is visited, so we should not write C. Next F, right? Next, no adjacent nodes. Again C is visited. Again A is visited. B, and then we have visited D. No adjacent nodes. Backtrack B, already there. No E. So E, there are no adjacent nodes. again backtrack to B. B is there, backtrack to A is there. So there are no adjacent nodes, any other adjacent nodes. So this is the DFS of a given tree. So right here. Okay. So this is the DFS for the given graph. Right? Now we'll go with the implementation part. So for implementing this one, we will use the stack. So for the step one, consider a stack and consider the DFS expression. Right? So starting node, push the starting node into a stack. So A will be presented here. So A is pushed here. Now pop the A and place that in the DFS expression. Right? So this is the DFS expression. So step 2. In the step 2, so popping the A and placing A here. Now place the adjacent nodes. Place the adjacent nodes here. So we'll go with adjacent nodes B, C. Push the adjacent nodes of A. Push the adjacent nodes of A. So what are the adjacent nodes of A? B and C. So we can write B, first we can push the B and then C, or we can push C and B. So if you push C and B, the output will be different. So both are same. So here both are the adjacent nodes, we can visit any node. Right. So next step, we have to pop the, so already C is visited, so we have to pop the C and push the adjacent nodes of C onto the stack. So step 3, B, A and C. A and C. Now what are the adjacents of C? F and G. So F and G. Right? B, F and G. So we can write first, we can push first F and then G, or we can push first G and then F. Anything is correct. Okay. So I am pushing the F first and G in the next. Now remove the element and push the adjacent nodes of that node. So here G is a leaf node, right? So it doesn't have any adjacent nodes. So just pop that node and place in the DFS. So step 4, A, C, G, so B and F are there. B and F are there. A, C, G. Okay. Then step 5. Same. So here G is not having any adjacent nodes. Leave it. Now F. Remove the F and push all the adjacent nodes of F. So already the DFS expression is having A, C, G, and now we are placing F here. So F is also having no adjacent nodes. Leave it. Now B. Step 6. Stack is empty. A, C, G, F and B. So just pop the element and push the adjacent nodes of that element. So what are the adjacent nodes of B? That are D and E. So first I will push E and then D. So anything we can do. First D and then E, or first E and D, because both are the adjacent nodes. Right. So after that step 6. Now step 7. What we have to do? Again, pop the element and push the adjacent nodes into the stack. So here D is having no adjacent nodes. Just pop the element. So step 7, E, and in the DFS A, C, G, F, B and D. Right? Now, only one element in the stack. The same thing, apply the same thing. Pop the element from the stack and place the adjacent nodes of that node into the stack. Here E is also having no adjacent nodes. So just after step 8, the stack is empty and the DFS traversal is B, D and E. Right? So stack is empty. Stack is empty. Right? So don't get confused. Just I have written empty. Okay. Okay. This is empty stack. Empty. Right? So if you observe this one, we got the same thing. A, C, G, F, B, D, E. So by using the stack, we can implement this DFS approach. Right? So this is one way we can implement this one. So one more thing I just want to say here, both are the adjacent nodes. Need not worry to push the order of, pushing the order of nodes into the stack. So we can follow any order. So you can push B first and then C next. We can push first C and then B, so that we'll get a multiple number of outputs. So if you push first C, so here we have applied, push operation first on B, then C. So we got this one. If you apply first C, then B, we'll get the next one, another one, another output. So don't get confused, right? So hope you understood this session, a simple DFS approach, depth first search. For implementing this depth first search, we'll go with the stack. This session, we'll go with the another graph traversal technique, that is breadth first search. So which is called a BFS. So in order to implement this BFS, we'll use the queue data structure, which is a first in, first out queue. So let us take the same example and then the same procedure is followed. So here also we have to visit all the nodes only once. So we can assume the start from any node and then we have to start traveling and we have to visit all the nodes only once. The same thing, we'll take that A, B, so the same example I am taking, D, E, F, G. Right. So first, travel from A, so mark it as 1. So then visit the adjacent nodes, all the adjacent nodes. So first 1, and there is one more adjacent node, 1, right? Then coming to the next level, visit the adjacent node of B and then visit the adjacent node of E, backtrack, right, because there are no adjacent nodes here. So backtrack to A, again backtrack, come to C, so visit F and backtrack to C, visit G, backtrack to C, backtrack to A, so that all the adjacent nodes have been visited. So here we have to visit the nodes in level wise. So first complete the level top level, level 0, and then level 1, level 2, level 3. So top level we have to complete all the visiting all the nodes, then go with the second level, go with the third level. Now we'll go with the implementation. So here after visiting all these things, we'll get the same order A, B, C. So A, level 0, level 1, level 2. So level 0 visit the node, level 1 visit all the nodes B, C, Level 2, visit all the nodes D, E, F and G. So we have to visit all the nodes level by level. So that's why we call it as a breadth first search. Okay, so in the previous session we have seen a depth first search. We have to go in a depth. Right. Now we will see how we will get this one with the implementation of queue. So step 1. So this is a queue and this is a BFS. Q and BFS. So first, so let us assume this one is a start node. Okay, the same thing, start node is A. So A, right, insert A into the queue. So this is a queue. Okay, step 2, remove the element from the queue and place in BFS. So as it is a queue where we have to remove the element, so both the insertion and deletion will be applied on same end. Okay, so sorry, so deletion will be from front end, insertion will be from back end, rear end. Okay, so A is removed and placed in BFS. Now insert all the adjacent nodes of A in Q. What are the adjacent nodes in A? B, C. B and C. So this is a BFS and this is a Q. So in the step 3, and remove the element from the queue. So here we have to remove the element from the front end. We have to insert the element at the rear end. Okay, so we have to remove the element. So the C will be in the top and place here A, B. Now what we have to do? We have to insert all the adjacent nodes of B into the queue. What are the adjacent nodes of B? D and E. So D, E. So the insertion will take place at the rear end. So this is a front. At the rear I have inserted D, and next at the rear I have inserted the E. So at the rear end I am inserting the nodes, adjacent nodes of B, because we are removing B here. Next, in the step 4, remove the element from the queue. Remove the element from the queue. So C is removed because the element is deleted from the front end. So D, E, A, B, C. Now what is the element we have removed? C. Now place the adjacent nodes of C into the queue. Place or insert the adjacent nodes of C into the queue, because we are removing C from the queue. So what are the adjacent nodes of C? F and G. So insert them into the queue, F and G. So apply the same procedure. Step 5. Right. So already A, B, C are there. Now remove the element. So deletion will be done from the front end. So D is deleted and placed here. Now there are only 3 elements, E, F and G. And we have removed D. So we have to add the adjacent nodes of D into the queue. So here D is a leaf node. So here D doesn't have any adjacent nodes. So just ignore. Next, follow the same procedure. Step 6. So A, B, C, D, and remove the element. So element is removed from the front end. So E will be removed, and we have to insert all the adjacent nodes of E into the queue. So what are the adjacent nodes of E? There are no adjacent nodes. Ignore. So there are only 2 elements in the queue. Step 7. Remove the element from the queue and place it in the BFS. So what is the element? F is removed here and placed in BFS. And we have to insert all the adjacent nodes of F into the Q. So there are no adjacent nodes for F. So remove, just remove. Next, step 8. Step 8. So A, B, C, D, E, F. So G is removed. So G is placed here, and we have to insert all the adjacent nodes of G into the Q. So there are no adjacent nodes for G. So here Q is empty. So this is the Q and this is the BFS. So the same thing we got here, A, B, C, D, E, F, G, A, B, C, D, E, F, G. So this is how we can implement the BFS, breadth first search, using Q. So hope you understood. So here we are visiting all the nodes level by level. So we have to visit all the nodes in level 0, then only we have to go with the level 1, then only we have to go to the level 2. Right? So here A is in level 0, so we have visited A in level 0. In the level level 1, there are 2 nodes which are adjacent to A. So A, B, C. So we have visited B and C. And then we will go with the level 2 because only 2 nodes are there in level 1. In the level 2 there are 4 nodes and we have to visit all these 4 nodes before entering into the next level. So visit all these nodes because all these nodes are adjacent to B and C, all the nodes of level 1. So D, E, F, G. So we are visiting D, E, F, G and go with the next level. So there are no other levels, right? Because level 2 is the last level. So this will be the answer. And this will be implemented by using the Q. Just insert the node into the Q and then first insert the node into the Q if the Q is empty. If not, remove the element or remove the node from the Q and enter into the BFS. Place it in the BFS and insert all the adjacent nodes of that particular node into the Q and follow the same procedure. So first we have inserted A and we have removed the A and placed it in the BFS, and we have to insert the elements of adjacent nodes of A into the Q. There are 2 adjacent nodes B and C, so B and C. Right? In the next step we have to remove the element from the Q. So where we have to remove the first element from the front end. So from the front end we will remove the node from the Q and we will insert all the adjacent nodes of that particular node into at the rear end. Right? Because here we are using the Q, all the insertions will be done on front end, all the deletions will be done from the rear end. Right? So we have to delete the element and we have to place it in the BFS. So this is a very simple traversal technique, BFS, breadth first search. Right? Hope you understood this simple technique.
So first let us see what is this spanning tree, and then we'll go with the construction of this spanning tree. So a spanning tree is a subgraph. So we all know about the graphs. So graphs are nothing but connected nodes with the edges with the cycles, right? So the spanning tree is a subgraph of a graph with the vertices and edges. So a graph will be having the vertices and edges with the cycles, right? But here the tree means it's a subgraph with no cycles. With no cycles. So here if it is not having any cycles, we call it as a tree, right? Now, so we need to follow a few points or a few rules while constructing this spanning tree. The first one is, so the spanning tree should connect all vertices of a graph, right? So it should contain all the vertices which are available in the graph in the spanning tree. And the second one, if graph is having n vertices, then the spanning tree should have n minus 1 edges, right? So n vertices in the graph, then spanning tree will be having n minus 1 edges. And the third one should not contain any cycles. So we need to follow these rules while constructing the spanning tree, right? So let us take one example, so graph, and we'll see how to construct the spanning trees. So first we'll consider the graph and then we'll construct the spanning trees from that particular graph. See, so we have to follow all the rules, right? So let us take an example with a 4 nodes. So A, B, C and D. So these are the 4 nodes and this is a connection between all these nodes. So this is a graph, okay? So edges, vertices and cycles, right? So now we should construct the spanning tree. So what is the first rule? First rule is number of vertices should be equal. Number of vertices must be equal in both the graph and spanning tree. So we have to connect all the edges. We need to connect all the edges. So I am writing all the edges here. Next, so these, if there are 4 vertices, we should connect with 4 minus 1 edges. So I will connect this one. So A to B, A to C and C to D. So this is the construction, right? So you can observe here, here we are having a 4 vertices and the edges are 4 minus 1, that is 3 edges. So this is one spanning tree. And another case, let us see A, B, C, D. So let us consider this one. So this is also a possible spanning tree from this particular graph, right? So because all the edges, all the vertices has been connected and the number of edges are n minus 1, that is 4 minus 1, and there is no cycle, right? And one more possibility. So this is one more possibility, right? So here also all the 4 vertices has been connected with n minus 1 edges, and there is one more possibility here. So this is one more possibility. Here also all the 4 edges, 4 vertices has been connected with 3 edges, because we are having 4 vertices, so the number of edges must be 4 minus 1. So this is the cyclic graph, and this is a acyclic graph. Acyclic graph is nothing but our trees, right? So all these are the spanning trees, okay? All these are the spanning trees, right? So one graph can have a multiple spanning trees. So here we can have the 4 possibilities, right? And if you consider one more example, like a triangle shape. So this is a graph. So we are having 3 vertices and 3 edges, so that it's a graph. So this can be constructed as, so A to B, B to C, A to C, C to D, right? And A to B and C. So these are all the different possibilities of spanning trees can be constructed from this particular graph, right? So hope you got an idea about this spanning tree. What exactly this spanning tree? Spanning tree is a subgraph from the original graph. So with n vertices and n minus 1 edges, right? So we need to follow the 3 points. One is all the vertices should be connected, and if n vertices are there, n minus 1 edges should be there, and there should be no cycles. So this is all about our spanning tree. Now, what is the minimum spanning tree? Now let us see the concept of minimum spanning tree. So minimum cost spanning tree. So it is called as a minimum cost spanning tree. So let us consider the graph A, B, C and this one. This is a graph, right? This is a graph. So each edge will be having a cost. Each edge will be having a cost. We can also call it as a weight for particular edge. Let us take here some 5, some 2, some 3. So the cost of an edge A to B is 5. The cost of an edge from B to C is 3. The cost of an edge from A to C is 2. Now construct the possible spanning trees. So the possible spanning trees are A to B, B to C, A to B, A to C, A to C, C to B. So these are all the possible spanning trees, right? All the possible spanning trees. Give the edges here. So 5 and 2, sorry 3. And here 5 and 2. 3 and 2. So now you have to, so you can observe here all the vertices has been connected. Okay, all the vertices has been connected, and here also all the vertices has been connected, and here also all the vertices has been connected. Right. So here you can see there is an edge A to B, B to C. There should not be a cycle, right? So here it is A to B, B to C. So if you add one edge from C to A, so what happens? The starting vertices and the end vertices same. That means it forms a cycle. So we should not connect this one. So that's why we are not connecting, and this is a spanning tree, right? Now cost for this spanning tree is 5 plus 3, 8, because there are two edges with a weight 5 and 3. The cost of this particular spanning tree is 8, and the cost for this one is 7, 5 plus 2. So the cost for this one is 3 plus 2, it's a 5. So you can observe here, for every spanning tree we are finding the cost. So here the cost is 8, cost is 7, cost is 5. Now we need to select the minimum cost spanning tree. So we will select the minimum cost spanning tree. That means the tree with a minimum cost of edges, right? So minimum weighted edges, the tree with the minimum weighted edges, right? So this will be considered as a minimum cost spanning tree. This is a minimum cost spanning tree, right? So hope you understood this one. So in this session we have seen about what is a spanning tree and what is a minimum cost spanning tree. So in today's session we'll discuss about how to find that minimum cost spanning tree. So here there are two approaches to find the minimum cost spanning tree from a graph. So that is, one is a Prim's algorithm, another one is a KRUSKAL'S algorithm. So in today's session we'll discuss about the Prim's algorithm. So before applying the Prim's algorithm on the graph, make sure that the graph should be weighted, connected and undirected. So unless the graph is weighted, connected or undirected, so we can't apply the Prim's algorithm. So make sure the first point before applying the Prim's algorithm. So the graph should be weighted, connected and undirected. And coming to the steps. So first we need to consider any vertex, because so we know the spanning tree definition. Spanning tree is a subgraph from the graph without any cycles, consisting of all the vertices of a graph, right? So consider any vertex of the graph. And the second step, find all the edges from the selected vertex to all the new vertices. So find all the edges. So among all the edges, you need to select the least weighted edge. So among all the edges, we need to find the least weighted edge and include it in a tree. So we need to construct a tree for that selected vertex and give in the least weighted edge. And if the least weighted edge forms a cycle, so if you include this least weighted edge into a tree and if it forms a cycle, then simply discard. So if forms a cycle, then simply discard that one and consider the next least weighted edge. So once you find the least weighted edge, you have to include it in a tree. So after including it in a tree, if it forms a cycle, simply discard that one and consider the next least weighted edge and include it in tree. And the third step, repeat the same step 2 until all the vertices are included in a tree. So once all the vertices are included, automatically that will be the minimum cost spanning tree, right? So this is how we need to find the minimum cost spanning tree with a Prim's algorithm. So here now we'll see an example and we'll find the minimum cost spanning tree by following all these rules. So let us take an example. So consider one graph. So consider this graph. So let us take some weights. So let us take these weights. Okay, this is a graph. Consider this graph. And we need to find the minimum cost spanning tree for this particular graph. So what we have to do, first consider any vertex. So I will consider A. I will start with A. So this is a A. So I have included this one in the spanning tree. Now consider all the edges from A. So you can see A to B with a cost of 2 and A to C with a cost of 3. Right? A to B with cost 2, A to C with cost 3. So we need to select the least weighted edge because A is having two edges. One is from A to B, one is A to C, A to B, A to C. So consider the least weight. So this is the least among these two. So we need to add this B to the spanning tree. Now the spanning tree will be A followed by B. So with a cost 2. So this is the tree. Now what is the new vertex here? B. So what is the remaining vertex? Consider this one A to C with 3 and consider the edges from B, right? So from B there is a vertex from B to A which is already covered, right? Because this is a undirected. Okay, this is a undirected. So B to A is covered. So we need to consider B to C and B to D. So B to C with a cost of 5 and B to D with a cost of 3, right? B to A, B to C, B to D, right? Now what happens among this one we are having a two edges with a minimum cost 3. So you can select any edge, no problem. So I will select this one B to D. I will select this one B to D. Now the tree will be A, the tree will be A followed by B, B to D. So the edges are 2, 3. Now the spanning tree becomes this one. So in the first step the spanning tree is this one. That means only one vertex. In the second step, so first step, second step, and this one is the third step. Now consider the remaining edges. What are the remaining edges? A to C with a cost of 3, B to C with a cost of 5, right? Now D is added here. Now consider the edges of D. So you can see D to B which is already done because of undirected, right? So you can simply use this one bidirectional, right? So B to D is completed. Now D to E. So D to E with a cost of 2 and D to F with a cost of 3, right? So the edges of D are D to B, D to E and D to F. So among the D to B is completed, right? Now among these what is the minimum cost? So this one, least weighted edge. So consider this one. Now the spanning tree will be A, edge to B, edge to D and from D to E. So the cost is 2, 3 and 2. Cost is 2, 3 and 2, right? And next, what are the remaining edges? Simply write here A to C with a cost of 3, B to C with a cost of 5 and D to F with a cost of 2. Now E is added. So what are the edges of E? E to D, E to C, E to F. So E to D is completed now. Just discard that one. E to C. So E to C is not there. So we can write the edge E to C with a cost of 4. And E to F with a cost of 5. E to F with a cost of 5. E to F, right? Now among this one is the least weighted edge. Least weighted edge. D to F. So see, our graph, our tree will be A, B, D, E and F, right? So this is 2, weight 3, this is again 2, now again it's a 2, again it's a 2, right? You can observe here whether all the vertices have been covered or not. A, B, D. So there is no, C is not there, right? So you can continue the process. So what are the remaining edges? A to C with a cost 3, B to C with a cost 5, E to C, D to F is completed. So E to C with a 4, E to F with a 5, right? Next, F, we have reached to F. So the new vertex is F. So write down the vertices of F. So F to D, F to E, right? F to E is completed. So F to D with a cost of 3. Now you can see among all these things, what is the minimum? A to C or F to D, right? F to D is also completed, right? F to D is also completed, so you need not go with this one. And one more thing is F to E. So that is also completed. F to E, we have written F to E here, right? So now among all these things, what is the minimum cost? A to C. So consider A to C and observe whether it is giving the cycle or not. It forms a cycle or not. So if you apply A to C, it doesn't form the cycle. So consider this one. So A to B, D, F, E, C. Right? Now you can give the weightage 2, 3, 2, 2 and 3. So you can observe here A to B with 2, B to D with 3, D to F with 3, D to F with 3. So D to F 3, okay, D to F is with 3. So this is D to F with 3 and then D to E with 2 and A to C is 3. So you can observe here all the vertices have been constructed, that means included in the tree. So A, B, C, D, E, F. So here we are having total 6 vertices. So all the 6 vertices have been included. And now you can observe here the remaining edges. What are the remaining edges? So consider B to C with a 5 and E to C with 4 and E to F with a 5. So if you consider B to C, so if you add a B to C, it forms a cycle. So we have to discard this one, right? E to C 4, E to C. If you just connect this edge, again there is a cycle. So A, B, D, E, C, A. So again you need to discard this edge. And E to F, again if you connect this edge E to F, again a cycle forms. So again we need to discard these edges. So we have to discard these edges so that we can have this one. Okay. So hope you got this one. So I think these things are not clear. So I'll write the edges here. E to C with a 4 and E to F with a 5, right? So I think now it's clear. So we have to consider from the single vertex, you can consider any vertex, and consider the edges, all the edges from that vertex to new vertices, and consider the least weighted edge. Okay, and continue the process until all the vertices will be connected. So this is the spanning tree, minimum cost spanning tree for the given graph. What is the cost here? So you can observe the cost. I will write here. Cost is equal to, so what is the cost? 3 plus 2 plus 3 plus 3 plus 2. 3, 2, 3, 3, 2. So what is the total cost here? You can observe. So 5, 8, 10, 13. So 13 is the minimum cost for this particular tree. So the cost is 13. The cost is 13 to construct this particular spanning tree. So this is the procedure we need to follow for Prim's algorithm. Okay. So consider a graph, and finally we are getting the minimum cost spanning tree. So we'll get a many spanning trees from this graph. So as we discussed in the previous session, right? So we can get a many spanning trees from this graph, but we need to find out the minimum cost spanning tree. So this is the minimum cost spanning tree obtained from this particular graph. So hope you understood this one.
So in this session we'll go with one more example. So let us consider this graph, and now we are supposed to find out the minimum cost spanning tree for this particular graph. So just recalling the steps, the first step we can consider any vertex, and the second step we need to find out all the outgoing edges from that vertex to new vertices, and consider the least weighted edge and include it on a tree. And after including the least cost weighted edge on the tree, if it forms a cycle, so we have to discard and we need to go for the next least weighted edge. Right? And we need to repeat the same thing until all the vertices are included in a tree. So let's start with this one. So this is a Prim's algorithm. So by using this Prim's algorithm, we are going to find out the minimum cost spanning tree. So first we need to consider any edge, right? So the first step I will go with here. So consider A. Now what are the edges from this A? So edges are like A to D with a 5, and A to F with a 7, and A to B with a 14, and A to C with a 21. So you can see from A we are having a 4 edges: A to B, A to D, A to F, A to B, and A to C. Now the next step, we need to select the minimum cost edge, right? Least weighted edge. So among these, this is the least cost edge, right? So consider this one. So our next one will be A to D. A to D with a cost of 5. A to D with a cost of 5. Now, what are the remaining edges? Simply write down all the edges. So, one is A to F with a 7, and A to B with a 14, and A to C with a 21. Now, consider the edges from D, right? Because the new vertex included in our tree, D, so write down the edges from D. So, two edges are there. D to A already done. So D to F with 13, D to F with 13, and D to E with 22. D to E with 22, right? So among all these edges, so this is the first step. So among all these edges, what is the minimum cost? So 7, 14, 21, 13, 22. So this is the minimum cost. So consider this one. Okay, consider this one. Right? Now, the graph the tree becomes A to D with a cost of 5, and from A to F, so the next cost is A to F. So A to F with a cost of 7. So what are the remaining edges? What are the remaining edges? See, after this one, what are the remaining edges? You simply go with this one. So A to B with a 14. Next, A to C with a 21. A to F. So this already happens, right? Sorry, D to F. Okay, D to F. So D to F with a 13 and D to E with a 22. So now we are having a one more vertex, that is F. So now consider the edges of F. So from F we are having how many edges? So 1, 2, 3, 4 and 5. So among all these things, F to A we have completed. So F to D or D to F. This is a bi-connected, so F to D or D to F both are equal. You can simply leave. F to E with a cost of 15. F to G with a cost of 18. F to B with a cost of 2. So these are the edges from F. So among all these things, consider the least cost weighted edge. So among these, this is the least cost weighted edge, right? Now the tree will be A, D, F, B, right? So this is 5 and this is 7 and this is 2. Now our tree is like this. Okay, tree is like this. Now the new vertex added here, and consider all the remaining edges. Okay, consider all the remaining edges. So what are the remaining edges here? So all these are the remaining edges. A to B with a 14. Next A to C with a 21. And D to F with a 13. And D to E with a 22. F to E with a 15. Next F to G with 18, F to B with 2. So our tree consists of a new vertex B. Now consider all the edges from B. So from B we are having only two edges, B to C and B to G and B to C, B to G, B to F and B to A. Now B to A, so there is already covered. B to F already covered, right? So we should not consider this one because we have already done, right? So this is already done, so we should not consider. So B to F, there is no edge. So B to G, 19. So B to G with 19 and B to C with 15. B to C with 15. Consider the least. Consider the least among all these things. What is the least one? So this one is the least. D to F is 13. So D to F is 13. So if you consider D to F, so it forms a cycle. You can observe here. It forms a cycle. So we should discard this D to F. We should discard this D to F because if you add this one, we'll get a cycle. So we should not consider this one. Next least. So there are two edges which are having the next least costed edge. So F to E or B to C. In such cases, you can consider any edge. Okay, here we are having two edges with the minimum cost. You can consider any edge. Okay, so I will consider B to C. I will consider B to C. Now the tree will be like this: A, D, F, B. Okay, so this is 5, this is 7 and this is 2. Now we need to consider B to C. What's the B to C here? Yes, B to C with 15. B to C with 15. Now consider all the remaining edges here. So A of B with a 14, right? So you can observe here. Okay, let us write down. No problem. Next, A to C with a 21, D to E with a 22, and F to E with a 15. Next, F to G with a 18, and B to G with a 19, because we should not consider this one because we have already done the edge from B to C. Now there is a new vertex here included in the tree. Now consider the edges of C. So C to B, there is no edge, right? So C to B, sorry. So already C to B there is an edge, right? So C to A, there is an edge here already covered. C to B already we have constructed in the tree. C to G is 3. C to G is 3. And C to E is 4. C to E is 4. Right? So among 4 edges from C, C to A is already written. C to B already considered in the tree. C to G and C to E. So this is the next one. So we need to select the least cost from this one. So which is C tends to G with a 3. So from C you can construct a G, so which doesn't form a cycle. So now, so I will consider here A with a D with a F, B, C and G, right? So the weightages are 5, 7, 2, 15 and the edge is 3 here. Okay, edge is 3. Now we have taken one edge, that is a new vertex G. So what are the remaining edges? See, you can observe here. So A tends to B with a 14 and A tends to C with a 21, D tends to E with a 22, F tends to E with a 15 and F tends to G with 18, B tends to G with 19 and C tends to E with 4. Now the new vertex is G. Now consider from G. So G, we are having 1, 2, 3, 4 and 1, 2, 3 and 4. So first G to F. So is there any edge? There is no edge. So we have to consider G to F. Okay. So let us consider here, right? So G to F with 18. Next, G to B. G to B. There is considered. We have considered, right? G to C. So we have already constructed the tree. So G to E is 2. G to E is 2. So these are the edges. Among all these things, consider the least. So this one is the least, G to E. Now construct the tree with this one. So A, okay, A to D, F, F to B, B to C, C to G, and the last one is G to E. G to E. So the cost, let us write down the cost. It's a 5 and it is 7, it is 2, it is 15, it is 3 and again the last one is 2. Right? So this is the tree and now you can observe all the vertices has been covered. So A, B, C, D, E, F and G. Right? So all the vertices has been covered here. So we can stop here and consider the remaining vertices. So consider this A to B. So we have considered G to E with 2 and we have included the edge. Consider A to B. If you consider A to B, it forms a cycle. So we should discard. A to C. If you consider A to C edge, right? Again, it's a cycle. D to E. So D to E, again it forms a cycle. F to E, F to E, again it forms a cycle. C to G, sorry, F to G, F to G, again it forms a cycle. B to G, again it forms a cycle. So C to E, it forms a cycle. G to F, G to F, again it forms a cycle. So all the edges has been covered and all the vertices has been covered here, and now you need to find the minimum cost of this particular tree. So this is the minimum cost spanning tree. So this is a minimum cost spanning tree. So you can see, so we are having all the vertices, okay, we are having all the vertices, and if the graph is having n edges, n vertices, the edges should be n minus 1. So how many vertices are there? 1, 2, 3, 4, 5, 6 and 7. 7 vertices are there. So it should have 7 minus 1, 6 edges. So 1, 2, 3, 4, 5 and 6 edges. So it satisfies the spanning tree, and you can apply, you can see this is the minimum cost spanning tree for this particular graph. And here the minimum cost, I will write here, I will write down here. So the minimum cost is, so how much? 5 plus 7 plus 2 plus 15 plus 3 plus 2. So how much it is? 12, 14, 29, 34. So minimum cost spanning tree, the cost of this particular spanning tree is 34. Right? So hope you understood. First you need to select any vertex and consider all the outgoing edges of that particular vertex to the new vertices, and select the minimum or least weighted edge from the among all the vertices, and if that edge forms a cycle in a tree, discard that edge and consider the next least cost weighted edge, and repeat the same process until all the vertices are included in the tree. So here you can see all the vertices are included in the tree. So we have stopped the procedure and we have checked all the edges. So all the edges, if you consider any one of the edge, it forms a cycle here. So that's why we have to remove all the edges. We need to discard all the edges, right? So this is how we can find the minimum cost spanning tree by using the Prince algorithm. In today's session, we'll see one algorithm to find the minimum cost spanning tree, that is a KRUSKAL'S algorithm. So in the previous sessions, we have seen one algorithm to find the minimum cost spanning tree, that is a Prince algorithm. So before going to that, let me revise the previous concepts, that is what is a spanning tree. So consider a graph, and a spanning tree is a subgraph derived from that particular graph. So with n vertices and n minus 1 edges, right? And minimum cost spanning tree means the spanning tree with a minimum cost. Okay, every edge will be having a cost. So having a minimum cost to construct the tree is called a minimum cost spanning tree. So in order to find out this minimum cost spanning tree, there are two approaches as we have discussed earlier, that is a Prince algorithm and KRUSKAL'S algorithm. So in the previous sessions we have seen the Prince algorithm. Now we'll see the KRUSKAL'S algorithm. So here the step 1, the first step means here arrange all the edges in ascending order. Based on cost. So every edge will be having their own cost. So we need to first arrange all the edges in ascending order based upon the cost. Right? Ascending order means lower value to the higher value. So we need to find the minimum cost spanning tree. So that's why we are using this ascending order. And then step 2, consider least cost weighted edge and include in the tree. Include it in tree. So consider one by one and just include that in a tree. And if the edge forms a cycle, just ignore and consider next least cost weighted edge. So every time we'll consider an edge and we have to include that on a tree. So if by adding that edge, if it forms any cycle, so just we have to ignore that edge and consider the next least cost weighted edge, because a tree should not have the cycles, right? So graph can have the cycles, but a tree should not have the cycles. So here we are using this KRUSKA'L's algorithm to find the minimum cost spanning tree, right? And the third step, repeat step 2 until all the vertices are included in a tree. So we know the spanning tree, right? So if the graph is having some n vertices, then the spanning tree should have the n vertices with n minus 1 edges, right? So similarly, we have to repeat the step 2 until all the vertices are included in a tree. So by following these steps, we can find the minimum cost spanning tree by using this KRUSKA'L's algorithm, right? So hope you understood this one, and now we'll see an example and we'll find the minimum cost spanning tree. So let us consider this example, and this is a graph and we need to find the minimum cost spanning tree. So what is the first step? We have to arrange all the edges in an ascending order based upon their cost. So here the least cost among these things are 2. So first let me write all the edges with a 2. So here you can see A to B. A to B is a 2 with a cost 2. So this is a bidirectional, because this is a bidirectional. We can simply consider A to B or B to A. Next, there is one more thing, that is a 2, D to E. Again it is a 2. Next, 3. So we are having A to C. A to C with a 3. And one more, B to D. B to D with the cost 3. And D to F. D to F with the cost 3. Then what about next one? It's a 4. So 4, B to E. B to E with a 4 and C to E with a 4. Next one is a 5. So B to C 5 and E to F is 5. So you can observe these are the edges arranged in an ascending order, because you can observe the cost, so from lower to higher. Now what is the first step? Consider each and every least costed edge and include it in tree. So first consider A to B. So I will construct the tree here. So A, B with a cost 2. Next D to E. So D to E. So D to E. So here it is a D. E. So what is this one? D to E, again 2. Next A to C 3. A to C, there is no C, so we have to add it. A to C 3. Next B to D. B to D. So it doesn't form a cycle, right? B to D. So just include that one. B to D, again it is 3. Next, D to F. So there is no cycle, so I will construct here F. D to F, it is 3. Right? Next, B to E. So if you give the edge here, B to E, it forms a cycle, right? It forms a cycle. So we should not consider this one. So this should be rejected. C to E. C to E. Again, if you form an edge, if you give an edge, again it forms a cycle, right? A, B, D, E, C, A. So we have to reject that. B to C. B to C. Again, if you form an edge, so it forms a cycle. So we have to reject. E to F. E to F. If you consider the edge here, again it forms a cycle. So you have to reject. So you can see in our graph there are 6 vertices. 6 vertices, and our spanning tree consists of 6 vertices. 6 vertices. Right? And here the edges 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay. So 3, 6, 7, 8, 9 edges. So there are 9 edges. You can observe here 1, 2, 3, 4 and 5. So 5 edges, which is nothing but vertices minus 1, right? If there are n vertices, there should be n minus 1 edges. So it satisfies. Now you can observe all the vertices are covered. So we can consider this as a minimum cost spanning tree, which can be represented as MST, minimum cost spanning tree. So now what is the cost here? Consider cost here. So cost of this one will be 3 plus 2 plus 3 plus 3 plus 2. So the cost will be 5, 8, 11 and 13. So cost is 13. So the minimum cost we can create or construct the spanning tree is with 13. So you just remember this is the same example we have taken in the PREORDER algorithm also. So there also we have constructed the minimum cost spanning tree with a cost of 13. So once just observe the session. So I will post the link in the description so you can follow that one. So that is the procedure of PREORDER, and this is the procedure we need to follow for the KRUSKAL'S. So this procedure is KRUSKAL'S algorithm. Right? So first we have to arrange all the edges in an ascending order based upon their cost, and then consider each and every edge and construct a tree. And if by adding the edge to the tree, if it forms a cycle, just ignore that and consider the next least cost edge. Right? So we have to repeat that one until all the vertices are covered. So here there are 6 vertices. All the 6 vertices have been covered with a cost of 13. Right? So hope you understood this one. So this is a KRUSKAL'S algorithm to find the minimum cost spanning tree.